Okay, so today we're talking about routing architecture. Last week's reading were two papers. Well, one was clearly on routing architecture. We're going to talk about this one today. The other one was most about routing architecture. So it's in one of Altera's quite, most recent chips. There's one more architecture after this. We might get to this today. If not, we'll get to it next week. But basically, a big change in Stratix 10 was in the routing fabric. Okay, so for next week, Xilinx's latest architecture. They've got multiple versions of this now, but Versal, lots of interesting features in that. So I would definitely read that paper. And Altera's latest architecture, which builds on top of that Stratix 10 paper, changes around some things, optimizes some more. So I'd definitely recommend reading both of these papers and submitting summaries on them. Both good papers. And we're getting towards the end of the term, so there'll be a few more papers, but probably only 2 or 3 more after this. So after those two, so if you're kind of going, do I need to read them? You should read them. You should do the questionnaire. Okay, administration. I saw someone on Piazza asking when is the course end. So there's no lecture December 2nd because I'm out of the country at a conference. But we had a recorded lecture during reading week, so it's all good. And then the end of term, we'll have a test at the start of this time slot on December 9th, and that's it. After assignment 3, there's one more assignment coming, which is not as hard on purpose. It's getting towards the end of the term, so it won't be as big as assignment 2 or 3. So that's kind of what you got going. If you're trying to make travel plans, December 10th is open season from my point of view. So hopefully that doesn't hold up anybody's plans to go back and visit family. Okay, course concept maps. So we've been talking about the details of FPGA architecture. We talked about logic blocks. We talked about RAM and DSP blocks, 2 of the other really important kinds of blocks. And now we're going to talk about routing. Before I go there, any questions about anything we talked about last week? Talked about lots of stuff. It's all completely clear, okay? Or maybe it's all completely fled your mind, okay? I'm going to choose to believe it was totally clear. Before we get into routing, there's like one last thing that's kind of on the boundary between routing and function block architecture. So that I didn't get to last lecture. Okay, so we talked about logic blocks, RAM blocks, DSP blocks. What about these other things that are less numerous, but we have these protocol blocks, things to make PCI Express or Ethernet more efficient. Instead of implementing it all in soft logic, it's pretty common to have that. We might have hard processors and their peripherals. So these things where we might have only like 1 or 2 or 5 of these kinds of blocks. How do we decide whether or not we should harden that? So I'll go through an example of that decision from PCI Express. So, because PCI Express is kind of interesting, and there are many generations of it, and it is generally hardened now in FPGAs. Okay, so let's look at what PCI Express looks like. It's got a few components to it. The first part of your PCI Express interface is called the Physical Media Attachment Layer, or PMA. And this is like basically a little bit of analog circuitry. People don't actually like building. How many people here love building analog circuitry? Okay, nobody? How many people are, no, one at least, okay. How many people do not like analog circuitry that much? Okay, and the rest are somewhere in between, right? Okay, so that's actually the way the world has gone. What basically circuit designers do, even very high-speed circuit designers, is they have to build some analog usually to talk to the outside world, but they try to get digital as fast as they can. And that's essentially what you're going to see here too. So what we have is data coming in. PCI Express is a high-speed serial standard, okay? So I told you that there are kind of 2 main ways that people talk to chips quickly nowadays. One of them is source synchronous, which we saw an example of with DDR. So you send the clock or a strobe alongside some data bits, and you use that clock to sample the data bits. That works up to a few gigahertz and, maybe 10 or maybe a bit more than 10 centimeters. So relatively short distances, reasonable speeds. For that kind of class of distance and speeds, it works well. You can build a lot of parallel signals. You can get good bandwidth at a pretty low area cost and a pretty low latency. If you have to go farther, okay, you have to go across maybe a backplane in a computer or a server. So maybe now you're not going 10 centimeters, you're going 30 centimeters, 100 centimeters, going over cables where it might even be like a few meters. You can't actually reliably transmit at a very high rate with source synchronous signals. You can't keep the clock aligned with those data signals through that longer interconnect very well. And you also are starting to have trouble building a lot of parallel wires, okay? So when your wiring starts getting expensive because you're going a long distance and you still need high bandwidth, you go serial. So that's what PCI Express is an example of. Ethernet's another one. So the first thing you do is you use differential pairs. Okay, so you use two IOs now to send one signal, so a positive and a negative. That makes it more immune to noise, and you can go longer distances. You do not send a clock. Okay, so there's no strobe, there's no clock for 8 data bits or anything like that in DDR. Instead, what you've done is, well, on the transmit side, which we'll get to in a minute, when you send the data, you make sure there are some transitions. You never send like a long sequence of just ones. Well, you never send a sequence where it's just all logic high or all logic low. You've got to have some transitions. From those, so you guarantee in the data format that there will be some transitions every few clock cycles. And what that does is it goes into a clock recovery unit. So when I'm taking the data in, first thing I do is I use two IOs. One's the positive, one's the negative. They go to a differential amplifier, so we detect, you know, if we've got a 1 or a 0 based on the difference between those signals. Now we need to recover a clock because we don't even know where our clock edges are. Basically, that's done with a phase lock loop. So a phase lock loop can generate a clock at pretty much any frequency you want. And there's a circuit that is basically watching for edges. And based on where the edges occur in the data, it knows, I'm getting pretty close to a clock edge. Slow my phase lock loop down a bit. Or I'm getting kind of close to the other clock edge. Speed my phase lock loop up a bit. So you're generating a clock off of the edges that are in the data. You need to know roughly how fast it is to set your PLL up, but then you basically are detecting the edges to train it, like to stay in the data window. Okay, this is really fast. Okay, so the version of PCI Express that I'm going to show you, because I was involved in the hardening decision of this, is PCIe Gen 3, which is like 8.5 gigahertz, so it's quite fast. The latest version of PCIe, I think Gen 5 is, I think it's like, I forget if it's 25 or 50, but it keeps going up, okay? So these are really short periods of time, and the data comes out at a very high speed. So we can't take something at 8.5 gigahertz and send it into the FPGA fabric. Like, so probably none of you hit an 8.5, you should not have hit an 8.5 gigahertz frequency on any of your assignments so far, okay? So the fabric can't even handle it. So you can design forever, you'll never get it done. So what you do is, basically we're going to have to like take this high-speed signal and widen it, right? So we'll do a serial to parallel conversion to get it down to a slower speed that's more manageable. And that happens right here, okay? So even like in, we haven't actually gone into the FPGA logic yet, but even the hard logic that we can build, standard cell logic that we're going to put in this block, it's not going to work at 8.5 gigahertz either. So we've got a little bit of logic, very high-speed analog and digital logic to figure out what the bits are, and then we immediately widen it, okay, to drop the clock frequency down and have a bus that's, say, 10 bits wide, 850 megahertz, and that's going to be a lot more manageable. Okay, so that's getting the data. Then there's the, I think, physical coding system or sub-block. What this is doing is basically doing things like error correction, okay? So you're going to have some error bits. So there's like an 8-bit, 10-bit decoder. So for every 10 bits in PCI Express, that really represents only 8. So you've got like 10, 24 possible sequences. Only 256 are valid. You figure out which of those 256 you got. And this is also what helps you make sure you've got some edges in your data. In PCI Express Gen 3, you just never send, you don't use any of the code words, any of those 1,024 possible sequences of 10 bits. You don't use any of the ones that would have too few transitions. Then basically, so I'm not going to talk about all of these things, but there's a bunch of blocks here to essentially align the data, error correct the data, and then we basically get into the protocol layer. So this is one layer above, which is let's figure out what this means. Okay, like this is a transaction with an address. So let's start looking at a bunch of the data we just got and figure out where is it supposed to go, what does it mean? Is this a read transaction, a write transaction, what address, etc. And then we can go out to the FPGA logic and we can do whatever else we need to do. And on the transmit side, we basically do the opposite. Okay, so some of this part basically has to be hard logic. Okay, this is like super high speed analog and a little bit of digital stuff. This part you could do in FPGA logic, but it's pretty high speed still, even though you've deserialized it. So you could do it. And you notice there's a bunch of muxes here. This is a highly configurable protocol, so most of these blocks can be skipped. Like you might or you might not do this. And then when we get up to the protocol layer, so even higher in the protocol stack, again, we can choose to skip some of these pieces or not. And the transmit side looks basically like the reverse of what I just told you. Okay, so we got to decide whether we harden this or not. So it's really high-speed analog. It's got a lot of protocols, so it's going to have a fair amount of configurability. And one of the things you do in hardening a block like this is putting in these bypass muxes, right? So again, these bypass muxes mean if the end user wants to do something different, they can take the data quite early out to the FPGA logic. They don't get to use all this other stuff. They have to decide if they need any of that. They'll build it in soft logic, but they basically can customize it. They can't bypass this first part because it's just impossible, right? You can't build this out of soft logic. This is another look at that same thing. Okay, so this is like your application. You want to talk to the outside world using PCI Express. You're going to need that low-level physical media attachment. There's no other option, so that has to be hardened. This coding sublayer is pretty low level, so you probably want that hardened too. But then you have these higher layers that are basically doing more and more of the protocol. And it's just another visualization that we can basically bypass parts of those protocols in case you decided you didn't like what the hard IP gave you. So you still have the flexibility to do it in soft logic. Okay, so should we harden this or not? So you kind of go through your checklist of first, is it big enough to worry about? If it's not that big, it's just not worth the engineering effort. This does take, this part of the PCI Express block that you could conceivably do in soft logic does take tens of thousands of LUTs and flip-flops. So it's pretty big. If we move that to standard cells, we don't have a lot of RAM in that. We don't have a lot of DSP. So the kind of shrinkage we're going to get is the shrinkage we get for soft logic, which is like your best gain when you harden it. So we expect this to be around 20x smaller. In fact, that's what we found, right? We did actually harden this, and it got about 20x smaller, which means it was mostly logic. That's where you get the biggest gain. Yeah, do you have a question?
I was just curious because you started off with sort of the logic size of the tens of thousands. When I think of, like, let's say DSP blocks, we harden the DSP blocks because arithmetic is such an important computation, I guess, in different FPGA applications. So if the, let's say, the application or the thing we're hardening isn't, let's say, very small, is the countermeasure only, like, do we then decide to harden only if, I guess it's very widely used?
Yeah, we want to pay attention to how often this is going to get used. So the fact that it's tens of thousands of lookup tables, well, if only a few people use it, we're still not going to harden it. Does that make sense?
Because I guess they go hand in hand.
Yeah, but on the other hand, if this took like 100 LUTs, you'd just be like, who cares, right? Like, just people can build whatever they want, but it's not. It's tens of thousands. They don't have to build it themselves, right? You can build soft IP, and FPGA companies do build soft IP. So before this was hardened, you could just use the soft IP, so you didn't have to go do a hand design, but you were going to chew up tens of thousands of LUTs. And those will get about 20x smaller. Okay, so there's a pretty big gain. There's another gain of, because this hard logic is faster, basically this is coming in again at like 8.5 gigahertz, and we're widening the data path to get a more reasonable clock frequency. So if you're going to go into the FPGA fabric in soft logic, you might do this at 250. If it's in a recent chip and you feel pretty good, maybe you do it at 400. So you have to widen this interface by a factor of, quite a bit, maybe 32 times. If I basically do more of it in hard logic, I get an additional area gain if I can clock it faster. So I don't have to, if I can run my hard logic at say 800 megahertz or say 750, instead of 250 in the fabric, I can actually make the data path 1/3 the width. So that's actually a factor of 3 additional area gain because my data path is narrower. So I've turned speed into area. So that gives us an even bigger gain from hardening it. The protocol's fixed and it's widely used. Okay, so we do expect a lot of people to use this. So that's a good thing. And actually the protocol at the time we were making the decision to harden this, PCI Express Gen 3 wasn't completely done, but the earlier versions were. So the protocol's mostly fixed with some risk that we might do a few of the wrong things for the latest version. But it's still mostly we think we know how to build it. There is a cost here. We have to add muxing and build all the options. So PCI Express now, I showed you it has a lot of different blocks in it. And people do have different flavors. So we have to put in these bypass muxes to allow them to skip various blocks. And at this time we're doing it, there were 3 generations of PCI Express. Now there are 5 or maybe 6. So it costs some area to support all those, right? You have to either build all of them with muxes to select them, or you have to factor out the common parts and build muxes. So what you build in hard logic is actually bigger, like more complicated than the IP core you would build in soft logic. Because in soft logic, you'll build just what you want, right? In hard logic, I have to build, this is what everybody wants with the appropriate muxing to skip all the other stuff. So that kind of eats into my gains, right? But it's not going to eat a fact. This was maybe 20x, narrowing the data path was maybe 3. Building, even if I build all 3 versions and I don't get to share much logic, that's only a 3x cost. So I could still get a big area gain. And so let's say I make it 20 times smaller. If 5% of my users use it, it's a net win. And for a protocol block like PCI Express, I expect it's going to be well above 5%. So it is a net win for this case. Yeah?
You mentioned that at the time when you hardened it, you didn't have, or Gen 3 wasn't available yet.
It was being specified. So you had kind of early specifications, but we had to put some extra circuitry in where we're kind of like, we don't know if it's this or that. We have to build both. This is like, you're basically building an ASIC when you harden it. So you kind of go, I don't 100% know if they're going to choose this option or that option. So you build both with some steering boxes. And you sometimes also make mistakes. It turns out like, oh, I thought the standard was going to end down here and we missed it. So we have to spin the silicon. So there is actually some risk. You do want to have the latest version of these protocol blocks because it's where you get the biggest gain. It's like kind of the most complicated one. But that latest version sometimes is a schedule risk, right? Where you don't, so you actually live the same ASIC experience. So.
Yeah, but I thought big companies like Intel, AMD, they kind of like help with building the protocol themselves, right?
Yeah, and so does Altera and Xilinx. They'd be in this, but that means you're in the standard committee meetings. But if you have to tape this chip out to be on time for like the next product, you kind of have to make a choice. You could say it's not fully settled yet, I will not harden that. Or you could say, I think it's reasonably settled, I think we could put this in with acceptable risk.
I see.
Does that make sense?
Even though Intel, or like, let's say you're part of Intel and you're developing the Gen 3 protocol, you're still going to have like all of the details, so you have to.
Well, the protocol committees are basically, they are committees. So you don't know 100% what's going to come out of it until it's done. And on some of them, I think I mentioned this one other time, like there's a bunch of politicking in some of them, right? So some of these, like some of the 5G wireless standards, for example, would be a good example where some companies are further ahead on certain types of coding and certain kinds of MIMO antennas, and they really want that in the 5G standard. Because if they do, they have equipment that's ready to go, or even they've started shipping, and they might even have patents, right? That everybody else is going to have to license, which is maybe a bit unethical, but there have been lots of litigation around that kind of stuff. And other companies, they've been doing research in this too, and they've decided this would be a good way to do it, and that's what they started building their chip around. They're like not neutral, right? So it's not like, Ericsson is like, well, we've been building our chips with this standard, we got a bunch of patents in that way, but Huawei says they've been building their chips this way, and they have a bunch of patents there. Yeah, let's be nice guys, right? Let's just say, let's do it the Huawei way. Our CEO is not going to really care that I just said I gave us a handicap. Like, it can be quite high stakes. And sometimes the solution is you kind of go, well, you can do both. And again, the FPGA vendors tend to love that, right? So that you need more configurability. Okay, so PCI Express is now hardened in pretty much all FPGAs. It's become common enough that it definitely pays off. So let's look at Gen 3. So you have two things to specify at a high level what kind of PCI Express you're using. What is the generation, which basically says how fast is your signaling. And then you also say how many lanes. So a lane is basically a differential pair. Okay, so it's two IOs that together send one signal. And actually, I guess it's four IOs because it's each direction. So two IOs going in, two IOs going out. That means basically one input, one output. So that's a lane. People usually will use multiple lanes to get more bandwidth. FPGAs, this is configurable. So this is again part of that IP core. It has to have a bunch of different options because you also need to be able to allow different lane widths. So let's say I'm doing 8 lanes. So that would be PCIe Gen 3 by 8. It's pretty common. It's 8 gigabits per second, and it's full duplex, so both directions. So if I do 8 lanes, then I have 8 gigabytes per second kind of going into that hard IP block. So the FPGA fabric, let's say 250 megahertz is not too hard. So we could say any soft logic that needs to deal with the data coming out of this PCI Express or send data to it can run at 250 megahertz. Okay, 250 megahertz is not 8 gigabytes. How do I match these things? How do I match this bandwidth? Yeah.
I guess if you widen it further and further to use a factor that you should like as much as like however the factor you widen it by, you also cut the frequency by.
Yeah. So basically, you don't have to match this frequency of 8 gigahertz. You match the bandwidth, and this is part of how FPGAs wind up with like lots of clocks, right? And many systems wind up with lots of clocks, especially around the IOs. So I want to match this bandwidth. I'll do it at 250 megahertz. I'm going to have to use, let me think about that, 4 times 8. I should be able to do this actually. Yeah, 4 times 8 times 8. So that's 256. Okay, so 256 signals at 250 megahertz is going to get me that bandwidth. Okay, so I should just flip the slide. I did the calculation already in advance. And I need this both ways. So I need 256 inputs, 256 outputs. And that's what should go into this protocol block from the FPGA fabric. So now I need to think, well, how do I hook that up? So the average logic block, let's say I'm looking at, the example I'm giving you here is from the Stratix series. So it's 10 adaptive logic modules. They each are a 6-input fracturable LUT. The average logic block for this would use around 30 inputs. So the worst case one might use a bit more than that, but on average they use about 30, and about 20 of its outputs. Okay. So we don't actually want to create local routing hotspots. So if I take all of these inputs and outputs and just try to hook into this PCI Express block from a couple of routing channels, I'm basically trying to get way more signals to that one spot in my architecture than I am anywhere else. Okay, so remember we had this equation that our channel width is equal to lambda, the average number of inputs that are used by a block, times the average distance they came from, like they were routed, r, divided by 2, because they could be coming vertically or horizontally. So, and if I apply that to this logic block, it's like 30 inputs. I said the average distance in reasonable placement inches, maybe 4. So that's 120. I divided by 2. It says my average channel width might only be 60. Okay, and you guard band that a bit, and you actually get quite a bit wider channel than that. But if I basically if I try to hook all these inputs and outputs up to, the same area that a logic block would go, my lambda goes suddenly from 30 to 256. So I've got a routing hotspot. And I'm going to need a lot of routing failures around that point. You could try to fix that by saying, well, add more routing to the chip, but it's not a good solution. You're basically trying to solve a local congestion problem by changing your whole routing architecture. It'd be better not to create the local congestion problem. So what you want to do is you want to spread the routing demand for a block like this that has many inputs over more routing channels or pieces of routing channels so that it basically isn't any harder to route to than logic blocks. Right? Logic blocks is your most common block. You'd like to make everything else kind of look like a logic block from the way it works with the routing. So if I want to have just 20 used inputs to each kind of spot where I connect this. Let me show you what that looks like. Then I would actually only allow, I should have this spread over 13 kind of pieces of channel, like 13, I have like basically here 1, 2, 3, 4, like 13 logic blocks. And you can see they connect to 13 different pieces of vertical channel and 13 different horizontal channels. I basically want this block to look the same so that it presents the same number of inputs and outputs to each of these routing interfaces as a logic block would. So I can do that if I spread it over 13 kind of rows. And usually these are put at the edge of the chip because I want to have this connecting to IOs. So I put it on the edge of the chip and I spread my interface over 13 routing channels. This puts a lower limit on the perimeter of this block. So if this logic in the PCI Express block shrank really well, which it might, given what I just showed you, when I choose to harden it, I still have to say, well, I can't really do that. Like I can't make it, maybe only 2 logic blocks high, even though maybe the standard cells only need that area, because it's going to create too big a routing hotspot. So I have to stretch it to interface with enough routing channels that don't make a big problem for myself. And in some cases, that might cost me a bunch of extra area. And if this, so in PCI Express, it's a big win, so we still do it. But in some other blocks, if they weren't used quite as much, it might be enough to tip you from this is a win to this is a loss. Does that make sense? So it's another thing you have to think about when you harden a block, is what is the area of these routing ports, because that's another cost. You have to build these muxes to connect to the routing. And how big do I have to make it, right? Do I have to make the bounding box of it a lot bigger to get access to enough channels? And is that going to be what dominates my area? Yeah?
It's kind of a silly question, but why make the block bigger and not increase the channel width just for the edge? I know you want consistency in the routing, but I could just multiply the channel width just on that side by 13.
Well, okay.
I get that. But
Okay, so if you did that, you'd have more routing here, but you still have to get out to the rest of the fabric. So you still have a choke point. Let's say you make this channel really wide and you only connect to it in one spot. I guess that would allow you to distribute the wiring up here to other channels. So that is a viable option. You would take some extra delay to get up to these other channels, some extra area to build that wide routing channel, but you could do that. It's also a layout pain because you've now got a unique routing channel to figure out and put in. But it is a viable approach. In a sense, like if this logic wasn't that big, you might have this logic and then a whole bunch of wiring that effectively is a redistribution inside this block to connect to all these channels. And you just have to take that into consideration when you're doing the area analysis. Yeah?
Is the denominator of 20 just a good number of, a good channel width that we're comfortable with?
I did 20 because I had 20 outputs. So I decided to do, I decided to basically go, let's try to make sure we have no more outputs, okay? I could have taken 30 and said, let's make sure we have no more inputs than a logic block. And if I did 30, then I would have wound up that it was safe to, maybe do this in 9. Does that make sense? The truth is you don't need to perfectly match what a logic block does, especially because, logic blocks vary some, right? They don't all have 20 outputs that they use. They don't all have 30 inputs that they use. So I could push this a bit, right? So instead of doing 13 high, I might do 10. It's probably fine. If I decide to do 4, it's probably not fine. It probably won't show up for a while, but when the chip comes back, people have lots of trouble routing this. And there'll be a fun game of blame storming, right, about whose fault that is. And you would secretly know it's your fault, but you would try not to, you would try not to volunteer that information. So, yeah, it's okay to push it some. And you might choose to do that, saying I'll take a bit of risk, but not too much. Any other questions on this? Yeah.
do we need some sort of synchronizer circuit because we are connecting multiple parallel lines and there might be some butt screws or
You don't
clock
normally,
uncertainties?
yeah, you're transferring between clock domains, so you have to figure out how to do that. So what usually happens in a block like this is so it comes in, for example, at 8.5 gigahertz. You recover the clocks, you turn it into a digital signal, you demultiplex it, so you widen it, you put it on a clock that's maybe 1/10 of that. And then you will transition, before you leave here, you'll down convert it to a different clock frequency usually. Okay, so you might down convert it to 250 megahertz. If you're going from 850 to 250, you'll do that through probably a FIFO with 2 clocks. Okay, that's a safe way to transition between 2 completely unrelated clock frequencies. If I went from, for example, 750 to 250, then I could do it with like a synchronous transfer because I could make 1 edge for every 3. When you go to the main FPGA fabric, what's normally happening is there's a last bank of registers here that are on the same clock domain as you're going to use in the FPGA fabric. And that makes this last transfer like a synchronous transfer that you can timing analyze normally. There are lots of ways you could do it, but that way's pretty efficient because basically any clock domain crossing that you had to do, you did here in hard logic, which tends to take less area. And then you do your final jump into the FPGA fabric with just a simple clock-to-clock, well, register-to-register transfer on the same clock. Does that make sense? When you actually go to integrate this, I mean, next lecture I should talk about FPGA clocking. There was one of the last chips I worked on at Altera. The clock distribution inside this block is a bit different than the clock distribution in the soft logic. And the IC designers do have to watch what is the skew between those things and what's the uncertainty between them. One member of my team noticed, almost by accident, that there was basically negative timing margin for this transfer before the chip taped out. So that it was like the serial transceivers were basically going to be unable to talk to the core at full speed because of too much basically clock skew and clock uncertainty. It got fixed before tape out, but that was one where like it was relatively close to tape out, and it was like, oh, this is actually not going to work at any frequency. That would be unfortunate. So, but that's kind of a detail of the fact that the clock distribution here is generally done in a different way than the clock distribution here. And I guess organizationally, the people designing this block are effectively ASIC designers. The people designing this block are effectively like these FPGA designers. If they don't talk to each other enough, you can wind up with you didn't work out who took what timing margin. But it's kind of an organizational thing. Anyway, good question. I think I might have answered a different one, but anyway, I still thought it was a good question. Okay, so that's all I had to say about this block. Any other questions before we go on to kind of the heart of routing architecture? Okay. Okay, so I told you that routing is actually the biggest thing in the core of the FPGA. So we take away the IOs. And there's lots of different dimensions to this. So I'm going to define some terminology. So some of the things we need to talk about are what are the lengths of wire lengths? What are the lengths of the wiring segments that we prefabricate? We usually call that L. So in the architecture I'm showing here, all of the wires are, I think I made the wires length 3. Actually, I'm not sure I did. But anyway, an example would be you might have wires that span 3 logic blocks before they end. And yeah, actually I did do that. So this is a length 3 wire, and then there's another one, and so on. Another thing that we have to define is how many programmable switches are we going to put in? So maybe we can put a lot, maybe we can put a few. What's the pattern of those programmable switches, both between wires and between like to and from the blocks? And what is the electrical design of these switches and these wires? Okay, so how wide are the wires? What's their spacing? Do we use pass transistors? Do we use kind of a tri-state buffer made out of pass transistors? Or there are a few other ways to make this. So all those things interact. So it's a pretty highly coupled problem. Some terminology has been defined in the literature to try to be able to speak about these things a little more precisely. So we usually divide the switch pattern part into 3 pieces. So we have what we call an output connection block, which is the pattern from the outputs of blocks to routing tracks. So what's the pattern of switches that we put in place? The input connection block is the pattern of switches on the other side, right? Going from routing tracks, we have 2 of these routing tracks can connect to this input. So that would be a different routing pattern. And then the switch block is what defines how the routing wires connect to each other. So you don't have to define the routing patterns in these 3 pieces, and some architectures do mix them together. But a lot of architectures, you can split them into these pieces, and it can help you think about it a bit. Okay, so let's talk a little about connection blocks. Okay, so the connection block is how many wires does each output connect to? How many wires does each input connect to? And usually we give that a variable called FC, which is called the connection block flexibility. You often have different values for the inputs and the outputs. And this is just a simple skill testing thing. Okay, what are the FC values in this example? Okay, so if you can count, this is your question for you. But this is a check to make sure that people are following. Amir, I know you can count. You can't hide it. What do you think?
FC input is 3 and output is 2.
Right, so 3 wires on the inputs, 2 on the output. Excellent. Sometimes we also, because in architecture experiments, sometimes we change the channel width. So sometimes instead of defining FC as a number, we'll define it as like a fraction of the routing channel. So for the input, we could also say that the FC was W, right? It's all the wires in the routing channel. And for the output, we could say it's 2 wires, or we could say it's like 2/3 of the wires in the routing channel. And they're both correct. Okay, so how do we build this? Okay, how would you build this part? Electrically, the input connection block. Because the way we're going to look at these kind of architectures is modeling their area and delay. So we need to think about them not just as X's, but like circuits. What do we build there? So how would you build this? Yeah.
Pass transistor or like transmission gate?
Yeah, and then how would you arrange those? So you're building it out of pass transistors or transmission gates.
Wire, pass transistor, wire, and then you can take it in parallel and they're connected to the rest, and only one of them can, all of them can be active at a time, I guess.
Right. So, okay, so you're going to build them out of pass transistors or transmission gates, and what you're describing is a mux, right? Only one path will be active at a time. Does that make sense? So we're going to build, this electrical structure is a choose from one of many, so we're going to build it as a mux. If we're building like a large commercial FPGA, we're going to do full custom design, so we're going to build it out of pass transistors or transmission gates the way we saw on the whiteboard. So it's an FC input to one mux, and so I can just draw it like that. Okay, how about the output connection block? So we actually have multiple ways we could draw that. We could do that. So it's a bit more interesting. So what are ways we could build that output connection block? What do you think? Yeah. Yeah, so I could build it as a demux, so a whole bunch of like pass transistors basically again. Okay, and that's kind of what I've drawn here. So you said demux. I want a buffer. These routing wires are pretty capacitive, so I'd like to have some drive strength. So I'm going to make a reasonably big buffer. And then I can build a demux, so pass transistors that are independently controlled. I need independent control because I might want to go to multiple routing wires. Like if I have a net that has fan out, goes 3 places, I might want to connect it to 3 different routing wires. So the structure's a bit different. I need to make these pass gates pretty big too, because these are driving routing wires which are relatively capacitive. So everything in this one is kind of big. There are other ways I could build it. I could build tri-state buffers. Okay, so each of these switches here, I could basically build an independent. So basically for this one, I built one shared buffer, and then, well, I guess if I only have 2 output switches, I just build 2 of these. I build 2 pass gates controlled by independent SRAM. If I could also build it with tri-state buffers. Okay, so I've got an inverter here, so that's half my buffer, right? I don't really care whether it's inverting or not. And I've got an SRAM cell that controls these AND and NAND gates. If I put a 0 in this, then this NAND gate is going to 1, okay, which is going to turn this off. And this NAND gate this AND gate is going to 0, which is going to turn this off. Okay, so I put a 0 in this SRAM cell. I turn off this tri-state buffer. And something else can choose to drive that routing track. If I put a 1 in here, then basically I just get the inversion of this input signal, right? Like this signal just gets passed on to the gates with the proper polarity. So for example, a logic 1 comes in here, and I'm going to put a 0 there, logic 0 comes in, I'll put a 1 there. Okay, so it basically just inverts on the, if I put a 1 in there. Does that make sense? So there's a bunch of different ways you can build a tri-state buffer. This is a reasonable one. And it basically means I can build, switches one at a time, completely independently. There's another way you can do it. You can basically merge this output connection block electrically with the switch block. So you actually have to kind of consider both together using something called a direct drive switch or a direct drive mux. So one of the papers you were to read this week is a paper by Guy Lemieux, who's now at UBC, on exactly that. So I'm not going to show you that circuit, but there is another commonly used circuit that does this in a third way. Yeah?
I got a little lost in the figure of the tri-state. I can see two of the states. I just can't see the third state where it's like it's left floating. Where is the...
Okay, if I put a 0 here,
Yep.
okay, I just disable this switch. Okay, so I put a 0 there. Then no matter what I put there, this is going to be a 0, which means this is off. Okay, and no matter what I put there, let's see, let me think about this one. No matter what I put there, this is going to be a 1, okay, which means this is off.
I see, both turn off.
Yeah, so putting a 0 in turns off both the pull up and pull down. If I put a 1 in, okay, whoops. Okay, so if I put a 1 in, and I try to send a logic 1 in here, then I'm going to get, let me think about that. That's a 0. So this is going to be a 0. And this is going to be a 1, 1. So that's a 1 inverted as a 0. And this is going to be a 0. So this is going to turn on, and I'm going to get a logic 1. Okay?
Gotcha.
So it works.
I got confused because you said the inversion and the bits, but I didn't know what bits you talked about. Thank you.
Okay, good. Okay, so this is a trade-off. So connection block, if we make FC higher, we have more switches, which means that we have bigger muxes or more pass gates, which means we have a larger area. Our muxes also get slower, right? So the bigger we make, say, our input muxes, we already saw they get slower. They also load the wire more. So every pass transistor that you connect to one of these routing wires, because it's the input to a routing mux, adds some capacitance, so it slows your routing wires down. So it's all bad, okay? So I said there's a trade-off. What's the trade-off? So all this says I should just make FC really, really small, because it's all bad. I got to build more stuff. It's more capacitance. It's slower. It's all bad. What do you think?
Maybe it won't be, like your routability won't be as good.
Yeah, if I make FC too small, just nothing routes, right? Or like basically, as I make FC bigger, more wires can connect to each input. Same thing on the output side. So it means we get less blocking as we search for paths through our routing fabric. It's more likely we can actually get where we need to go with a certain channel width. So we can actually use a lower W and maintain the same routing completion rate. Lower W actually saves area. It's like less metal area. It's also less switches in the switch blocks between routing wires. So we get a smaller area. As we get a smaller area, our whole tile also gets smaller, which makes our wires shorter, which reduces their capacitance, which also gives us a speed boost. So it's a classic trade-off, right? Like we can't just look at this and differentiate it and say we know what the best thing is, because we have too complicated a function and it's pushing in different directions. Okay, so the way that people look for better, or look for a good routing architecture then is empirical. And this is a figure from one of my original VPR papers. So I've already shown you this, basically an updated version of this for VTR. But some of the routing results that I'm going to show you come from this flow where you go through a full CAD flow. And often what people will do is they will change the number of tracks, the channel width, okay? So changing the channel width you can't really do in a finished FPGA. So if your design doesn't fit in the ARIA 10 device you're targeting in assignment 1 or 2, you can't just change the channel width. But when we're experimenting with different FPGAs, we can. So we can say, let's try over and over again for some circuit and some routing architecture to route it with different amounts of routing. and see what's the minimum channel width that works. And that's what's done often in the literature. Now, you don't actually want, that'll actually get you how little routing you can build, but you probably don't want to build such a small amount of routing. The reason is because the router is like desperate. When it can just barely route things, it will take circuitous paths if it has to, and it could destroy the timing of your circuit. So that can be kind of misleading. So what is commonly done is you then, once you've found the minimum channel width for every circuit, you actually increase it some. So you might increase it by 20%, you might increase it by 30%. And what that does is you say, now I've got some spare room, because that's more likely what it would actually build. And my timing is more stable. And now you can basically evaluate, okay, how much routing area did I need to get to this somewhat comfortable point for that circuit, and how fast is it? And you can repeat that for a whole bunch of benchmarks, average it, and get a figure of merit for the circuit. So there's an alternative flow where, so some people said, well, wait a sec, what is this min-trax? Don't do that. Like what? Each circuit shouldn't get to choose how much routing it wants. What you should do is the architecture should just say the channel width is like 200, okay? And all circuits have to live with that, because in the end, that is what you build. So that's the alternative flow that sometimes people use, is they just, the routing architecture includes what is the channel width. It's not allowed to be adapted for different circuits, and you just run the same thing, but you don't have this loop. And at the end, you still get an area, and you still get a delay for every circuit. The benefit of that is, in the end, you really do have to pick a channel width. The downside of it is, from a point of view of like routability analysis, it's only the hardest circuits that contribute now. Like most circuits will just route easily, and only the hardest 3 or 4 or 5 are actually going to tell you whether you've chosen a good channel width or not. So there's no one best answer to this. What we did at Altera is we did this minimum channel width style of search when we were broadly searching this space, because we kind of wanted all the circuits to contribute to the average. But once we zoomed in on the most promising architectures, we would actually say, okay, let's pick a channel width, and let's check if they all route well and how fast they are. So we would kind of do a mix. I know some of my colleagues at Xilinx basically are like, do not do this. Why are you doing that? Just like pick a channel width. So if you want a controversy, there's a small controversy in like routing architecture. Okay, so let's talk about a few results from that flow for FC. So the best value of FC basically depends on whether your input pins can be swapped or not. So if we think about those logic clusters that we studied a while ago, where we have crossbars on the inputs, if you have a full crossbar on the input of your logic block, you actually, the router doesn't have to get to a specific block input. It can get to any of the block inputs, and it'll basically get steered by the local routing inside the logic block to the right LUT inputs or BLE inputs. And that matters. So what various studies on this have found is that a good value for FC, if you have just one, like a very small logic block, like one LUT, is close to W, right? Just make almost all the, like either all the routing wires or close to all the routing wires can reach the input pins. But if you make the block bigger, so let's say you had a logic cluster and you had 4 or 10 logic elements in it, or BLEs in it, and you had this local interconnect that allowed you to, once you hit an input of the cluster, you could get anywhere you wanted, then this is overkill, right? You don't need to do this. You could instead basically reduce the FC inversely to essentially the number of things in the logic cluster, okay? The basic reason why is because these larger clusters, when they have very flexible local interconnect, like a crossbar, you have what are called logically equivalent inputs, right? The router doesn't have to get to input 3, it can get to any input, and that'll get it after the local interconnect to the right spot. So if we use some of the terms we had here, if you remember back to how many inputs should we build for those logic clusters, we found that the LUT size is k over 2 times n. If we have n things in there, was a reasonable number of inputs. If those are all equivalent, well, the number of inputs that a wire can reach is the number of inputs times the probability of having a switch. So the number of inputs is just this. k over 2 times n. And the probability that there's a switch is just if I make my FC equal to this value, I just divide that by W, the number of wires. The probability of a switch is 2 over n. Basically means every wire can actually reach k inputs of the logic block. And because it's reaching any input is fine, this is enough, right? As the channel gets wider, we don't need to make the wires able to reach more and more and more different inputs. It's enough to just kind of keep it fixed at this relatively small number. But that is because we have this local interconnect. If we didn't have this local interconnect that could kind of finish the last stage of the routing, this wouldn't be true. In this style of architecture where I have crossbars in the input, actually you can also swap around the outputs. And that means that we can also make the outputs their FC relatively low too. So W divided by N. So as we make more things in the cluster, if the local interconnect is quite flexible, we can scale down the FC on our inputs and outputs to get more use out of our local routing. Hopefully that made sense. So, okay, yeah.
So you say that these, like FC will be, like let's assume we're using FC of 0.5 times W. Would each tile have the same exact pins connected to the output pins, you know what I'm saying? Or would they like kind of randomize it for like each CLB? Because I feel like that's also a layout. Like,
Yeah, so you can do it either way. So it's often the same for all of them, just for layout reasons.
gotcha.
But if you have automation in your chip assembly, it doesn't have to be the same. And there can be some advantages to not making it the same. When your patterns are really regular, you have to be careful that you don't create, like regular patterns are actually more dangerous than random patterns, because regular patterns you can wind up with the router having fewer choices. So I'll show you an example of that in a little while. But basically, one thing I've found over the years is you have to be careful of regular patterns that seem really nice, because they can lead to, that regularity can lead to actually more congestion. That when you go through all the options, there turn out to be fewer distinct options for the router than you thought.
Gotcha.
It's not always true, but it means you have to be really careful with regular patterns. Okay, so let's talk about the switch block. So in the switch block, we have this, so that was FC. How much do we connect to the block inputs and outputs? So we have FS, which is defined as a routing wire comes into the switch block, the point where two routing channels cross. How many connections do I get? Okay, so I end, how many switches do I have as I cross this routing channel intersection, the switch block? Okay, so I'm going to go. So this is showing for one. I've numbered the wires. Okay, so this is wire 0 or track 0, wire 1 or track 1, and same thing here in this channel. Okay, so I've got numbers on them. I'm just showing the switches that are coming off the end of this wire. So go to this wire and this wire. Here I'm showing all the switches. Okay, so I repeat that for every wire that went into the switch block. I'd get that pattern of switches. Okay, so this is another counting example. Anyone who was like, wait, I can count too, right? Like, could you call on me? So this is your chance. What is FS here? So be checking that people are following along. Yeah, what do you think? Yeah, so FS is 2, okay? Do you think this is a good switch block? So I said you have to really evaluate these things empirically, use a CAD flow, but you should have some intuition too. So do you think this is good or bad? Yeah, what do you think?
I think it's bad because it's hard to go into your direction. For example, if you're coming in from the left, from the right, there's no real way to go up unless you go to the right. There's no real way to go up.
So you're saying when I come in, if I come in from this direction, I gotta go down, or I could, maybe I can go left. I go left or down, but I can't go up. And for this one, I can go up or I can go right, but I can't go down. And you say you don't like that.
I don't like that.
Okay, so you know what I call this switch block pattern? I call this the TTC pattern, okay? So
Go left, you go straight.
that train is out of service. You are now going downtown. I don't really care where you were trying to go. That's where you're going. Yeah, so this is like too low flexibility. And for exactly the reason you said. It doesn't make any sense. And if you try to make your placement engine optimized for this, like you could say, well, that's software's problem, right? Just don't ever try to go down. But it's like, well, that's a really hard problem. Like, that doesn't sound good. So this is not flexible enough. It's just not going to work well. Yeah?
You also stay on the same plane. So for example,
Yeah, so that's another thing in here. So we'll talk about that in a little while too. But this one is just not enough switches. So FS equals 2 is not good. Yeah,
But even if you stay on the same plane, like if you can stay on the same plane but go in all directions, I don't know if that's the worst thing in the world.
You get congestion though.
Like you would get congestion, but like you also don't want to just have universal because then you have a lot of.
so I'm going to go onwards to show that because you guys are going, that's interesting. So I'm going to show more visual aids so people can catch up. So yeah, so this is not enough choices. So there's a bunch of papers on this. And they've shown that for length 1 wires, so I only go 1 unit between switch blocks, that the best value of FS is 3. Okay? 3 is enough. You don't need more. Now, since most of those studies were done, a switch design has changed, right? So some of the how we electrically build the switches has changed. You're going to see that in the direct drive paper. So I think you can interpret those papers as FS should be at least 3, but somewhat higher might be reasonable now. They found that somewhat higher wasn't terrible. It just didn't actually quite pay for itself. But we've actually gotten better at implementing switches in a cheaper way. You're going to see that in that direct drive paper. So I would say, it's at least 3, but if you go higher than that, that's also reasonable. The reason you need to have at least 3 is exactly what we just talked about. You at least can go straight, kind of turn left or turn right. Say I'm coming in from the bottom, right? I can go straight, turn left, or turn right. So at least have an option in every direction I could reasonably want to go. If I go below 3, I just can't do that, right? So you're going to wind up with a really bizarre routing fabric. Yeah, extra switches, so you do get more flexibility. Now you'll be able to reach 2 wires on some sides, or 3 wires, etc. So that reduces your probability of being blocked, but you do get more switch area. As I said, those earlier studies say it wasn't quite worth it. I think given that we've gotten better at making efficient routing switches, it might be worth it to some reasonable, 4 or 5 or 6 might now be reasonable. For longer wires, there's actually less studies on it because the main studies in this all worked on length 1 routing architectures. But basically at the ends of longer wires, it still makes sense that your FS should be 3 or more because otherwise your wire ends and you can't go every direction. And beyond that, it's not 100% clear. Probably you want FS to be a bit higher than this at the end of a longer wire because the wire is kind of expensive. So having a few more switches to reduce blockage is reasonable. Okay, how do we build this switch block? So traditionally, we build it out of either a pass gate. So we could build a pass gate here that connects these two. And the nice thing about that pass gate is bidirectional, right? So we build 1 SRAM cell, 1 pass transistor, and it actually implements both these arrows. I can go from this wire to this wire, or I can go the other way. So it's actually very area efficient, right? I get kind of a bidirectional switch, and it only took me 1 SRAM cell and 1 pass transistor. I could also, alternatively, if I want to do this one edge, or these 2 edges, I could build back-to-back tri-state buffers. Okay, and here I'm showing a different way to build a tri-state buffer. I can build some inverters. Maybe I need a couple in series because I need a lot of drive strength, so a little one and a big one. And then I could basically build big pass gates going everywhere I need to go. So here I might have 1 pass gate going there and another pass gate going there. And I'd basically implement 2 of these edges with basically that, okay? So that would get me, one direction. If I need to go in the other direction, I'd have to build a tri-state buffer going the other way. Does that make sense? And again, this is not the only way to build a tri-state buffer. This is like basically, a demux tri-state buffer that can be beneficial sometimes. I showed you the other way where you build totally independent tri-state buffers. That can be beneficial sometimes too. Yeah?
When we have multiple wires with different length, so do we connect them inside one switch block or for a specific wire length, you have a specific switch block?
You connect them, usually you consider 1 switch block, okay? And so you can do anything you want, right? And you'll usually have like wires of different length connecting to each other. You don't have to do that. I mean, you could say, look, wires of this length only connect to other wires of this length, but it's generally beneficial to have some ability to connect between different wire lengths because it gives you more options to kind of construct the exact length of wire you need in the routing. Does that make sense?
Yeah, so the switch block would be different for example, we can have 2 types of switch blocks.
You could, I mean, usually what you do is you make one switch block, but inside of it, you might have, it can be quite complicated to describe. So when you get into like the full, what is the full switch pattern and so on, of like a modern FPGA where you might have like 5 lengths of horizontal wires and 4 lengths of vertical wires, you would actually wind up with not one FS, but a whole bunch of different FSs. Like the horizontal length 4 wire connects at its end to 3 other horizontal length 4 wires, and it also connects to 2 vertical length 10 wires. Does that make sense? Like, I can describe that with just one number of FS, but it kind of obscures a lot of detail. And there are a few papers that go into that level of complexity, but most of that's done inside the commercial companies, where they basically use these architecture evaluation tools and they try all sorts of combinations of exactly what wires and what switch patterns. You'll get some chance to play with that in assignment 4. So if you're like, oh no, only the companies can do that? No, you can do some of it too. So, but they do it for longer. Okay, so basically I called this traditional because these are the 2 ways that people built routing switches until we got to direct drive switches. So we'll talk about that paper in a little while. Okay, so that was FS. And FS is kind of useful in thinking about how many switches you have, but it's not everything. You also want to think about the pattern of switches. So, and we think about what the pattern of switches is in the switch block and also the pattern in the connection block. So this is, somebody already mentioned this term. Whoops. Okay, this is auto advancing. It's telling me to go faster. Okay, so some of the kind of classic switch patterns, some switch patterns have no name. Like they're just super complicated, okay? And the ones in commercial FPGAs, generally that's what they are. They're like complicated and you'd have to draw them. But some classic simple patterns have names. So this one's called a planar switch block, or sometimes called like a disjoint switch block. So this wire, which is like in track 0, connects only to other wires in track 0. And the wire in track 1 would connect only to other wires in track 1. Okay, so the reason the thinking behind this switch block is that it should be easy to lay out. Okay, it creates a nice regular routing pattern that should be layout friendly. And it is kind of layout friendly, so that's true. So anything else you think about this? You like it, don't like it? Yeah?
Like, I guess to Alex's point, like, sure, it does lead to more congestion because you're staying on the same track.
So you're thinking that this could be harder for the router, okay? Because I basically, you know, am always, if I come in on this wire 0, I can only get to other wire 0s. Is that right?
Yeah.
Okay. And you're right. It actually does lead to more. It does lead to more congestion. Okay. And let's see if I can see why. Okay. Maybe I can draw this quickly. The reason why is not obvious. Maybe I have to explain this first. So this is actually a former, now a prof at UBC, but former PhD student here, Steve Wilton. So you make a new switch block, you get to name it after yourself. It actually is traditional. Okay. So I don't think he actually named it after himself, but other people named it after him. So he came up with this switch block. It has the same number of switches, and it looks almost the same, right? So this edge is actually the same as it was before. This edge is the same. All it does is it took what was a connection to this length 0, this track 0 wire, and it basically rotated it to be on track 2 instead. Okay, so it just moved one switch. What this does is now basically I have some ability to get to these track 2 wires, okay? And it's hard, it doesn't look, when you look at one switch block, it doesn't look any different, okay? Well, it's like I could get to 3 wires before, I could still get to 3 wires, who cares, right? It's just a different 3 wires. Where you get a difference is, hopefully this is visible, let's see. Okay, so let's say I'm going, let's say I come out of this block and I have a switch that allows me to connect to track 0, but I don't have a switch that allows me to connect to track 1. So I come out of track 0, and let's say I'm trying to go over here, and this block can connect to both track 0 and track 1, okay, on its input. So I could go down here. Let's see, I can switch onto something here and switch here. And if I'm using this planar switch block, no matter what I do, I'm going to stay on track 0. Okay? So, and if I went down this way and then came over here and then came up, I'd still be on track 0. Okay? I took a different route, but no matter what, I can never get off track 0. So if this is blocked, somebody else has used it, or maybe I don't have a switch there, I can't get around it. Okay? No matter what, I'm always going to wind up on track 0. If I change this to the Wilton switch block, basically how many turns I make and exactly what kind of turn I make is going to affect what track I wind up on. So if I go here and then down here, I made one turn down and then one turn to the left, and that could leave me on track 1. Okay? But if I did a turn down and then a turn right, I can wind up on a different track, or I can do this where I go down, then I go up again, etc. So based on exactly where I make how many turns I make and which ones they are, I can wind up on different tracks. And that gives the router more freedom to find ways around this blockage. So kind of a general principle when you make these switch patterns is essentially making them a little more irregular. Even if a human looks at them and goes, that looks a bit more ugly, it tends to give the router more freedom. Right? It can search through this graph and it can find if I do this and do this, this option turns out to be different than that option. Routers don't really like when a lot of their options wind up in the same spot. Okay? You're taking flexibility away from it. So yeah, these patterns, so you basically, when you're making switch patterns, scrambling them some is actually good if you have the same number of switches. So we basically at Altera, we made like an automatic switch pattern optimizer. And we found it could do a bit better, like somewhat better than a random pattern, but not that much better. But it did a lot better than some patterns that we would make by hand that we thought were clever. So some of the clever ones that are very regular are actually dangerous.
For the Wilton switch block, do you do that on a different track in every direction, or do you have something
The Wilton one just scrambles one of, it's designed only for fs equals 3, right? So it's only really defined that way. It scrambles one of those 3. So 2 of them actually go to the same track number. Let's go look at the paper to be sure of this, but I'm 95% sure that 2 of them in every direction always do the same thing as the planar switch block would have done, and the 3rd one goes to a different. Does that make sense?
And what about like just having a different track? Like, does it make a difference if you have a different track on all, like, get on a different track in all 3 directions?
That would probably be fine too. I think I just did that because it was kind of like, well, that's probably like, maybe that's more layout friendly than scrambling everything. And I have to go back and look at the paper. It doesn't scramble the straight through connections. I think it just scrambles one of the 2 other ones. But I'd have to look at it to be sure to make sure it didn't scramble both. Okay, so another thing we need to choose is how long are these wires? Because we have to prefabricate all the wires in advance. Okay, so we can make longer wires or shorter wires. So these are like length 8 wires that go 8 blocks before they end. These are length 4, they go 4 blocks before they end. So the long wires are good for long connections because I don't have as many switches. Whenever I go through a switch, I go through some kind of electrical switch, some transistors, it slows me down some. But short wires are good for short connections, right? I have more capacitance on this long wire. So if I'm going a long distance like this, okay, I minimized my routing switches, so that was good. But if I'm going a short distance, I've got all this extra capacitance hanging off that's just consuming power and taking delay to charge and discharge. And then if I do length 4 wires, well, so they're better for these short connections because there's not so much extra capacitance hanging off of them. For the long connection, they're not terrible, but I get this extra switch in the middle, which is generally going to cost me some speed. If the wire gets super long, right, there's some point at which this wire gets so long that it's so resistive that putting a switch in the middle is a good idea, right? Because you need to essentially repower the wire. But that is considerably longer than like length 8. You have to have a fairly long wire before that happens. In terms of like the metal area, these shorter wires, I can make more connections. So I can actually implement both these relatively short connections in one routing track. So I can make essentially 3 connections with these 2 routing tracks, and up here I can only make 2 connections, right? There's nothing left over here, right, to make this other connection. So if you use shorter wires, you can generally get a narrower channel width, like a smaller W, because you get kind of less wastage. Okay, so if you make a routing architecture with just one wire length, generally commercial architectures will use a bunch of different wire lengths now, but it's hard to start off talking about those. So let's just say you want to make one wire length. This is a study that's done in 22 nanometers. On the left axis is area delay product. So yeah, a mix of how efficient in area this routing architecture is and how fast it is. And on the right is just routing delay in nanoseconds. So lower is always better. And for both area delay product and routing delay, length 4 wires are the best, but length 2 is pretty close. Length 1 is too short. You wind up with too many routing switches, slows you down, wastes area. Length 8 is too long. You wind up wasting some of you need wider channels, which costs you area. And some of your connections are short, and these length 8 wires are basically slowing you down with extra capacitance. So kind of the sweet spot is in here. There are a bunch of earlier studies. So this length 4 being good kind of aligns with earlier studies in older process technology. But those earlier studies said length 2 was not as good, right? Length 2 is actually getting like close. Why do you think it's getting closer? Does that make any sense or not? So from an older process node to 22 nanometers, because one good thing is there's still some consistency, right? Length 4 is still good, but length 2 is getting better. So why? What do you think?
Maybe it's easier to make the switches.
So it's easier to make the switches? Okay, so the switch area is kind of getting smaller because the transistors are scaling well? Yeah, so that is actually true. The transistors are scaling very well compared to the wires. So that's true, yeah. Yeah.
Well, you kind of said it at the end, but in the newer processes, the wires, longer wires, they're becoming more expensive. Like they're more capacity.
Yeah, longer wires, well, you're dominated by wire capacitance more and more, and also you're starting to get hit by wire resistance. Okay, so wire resistance, I mean, it's always been a factor, but it's basically becoming a factor at shorter wires than it used to happen. Once you have enough resistance in the wire you're using, because you've gone far enough, it becomes beneficial to go through a buffer, right? It actually speeds you up. So yeah, those two phenomena are making shorter wires somewhat more attractive. And this is just like a picture of like, what does the metal stack look like? This study was using the middle of the metal stack. Okay, so you have to kind of think, well, for this piece of the study at least, the study looked at a few different things, but it said for the kind of workhorse routing wires where you have a lot of them, your fastest routing wires are way up here where they're really wide and really thick. They have the lowest resistance, but there's only so many of them. So it's assuming that these routing wires are built in the middle of the metal stack, so they're not the narrowest, but they're not the widest. So they have a reasonable amount of wiring resistance, which will tend to push you towards shorter wires, where you get a buffer more often. Yeah?
Is it possible that the previous studies, the architectures, like had smaller CLPs where you couldn't have as many like connections inside?
It's possible too. Yeah, that would interact as well. The logic blocks have been getting bigger. The electrical designs of the switches have also gotten better, which also, all those things will kind of push you towards wiring more expensive switches not as bad. So that makes sense. Okay, so let's talk about how we electrically design the switch block. Okay, so we can build I've already told you some of this. Pass transistors, we could build tri-state buffers in a couple different ways. So basically a big buffer and a big demux, or the independent tri-state buffers, where each has its own independent control. Or we can build this other thing, which I haven't talked about yet, which is called a direct drive switch. So direct drive switch is kind of the opposite of this tri-state buffer built as a demux. It's basically a pass transistor multiplexer followed by a buffer that you can't tri-state. Okay, so I can't turn this off. It's going to drive the wire no matter what. Okay, so I think, yeah, so I don't know if well, I'll pause. If anyone has any, yeah, what do you think of these actually? The paper from Lemieux is going to talk about some of these. What do you think about these switches? Any strengths, weaknesses? Yeah.
If a wire is always driven, it sounds like you can get a short circuit very easily.
Okay, so you don't like the direct drive switch, or you think there's something you got to watch out for it. So yeah, the direct drive switch is less flexible. I can't shut this off, which means every wire that I connect this to, I can only connect exactly one routing switch to it. Well, I can have multiple switches listen to it, but only one direct drive switch can drive it, because I can't shut it off. If it turns out that none of the routing wires that were kind of inputs to this want to drive that wire, it's useless, right? There's no other choices. So yeah, so this one is the kind of least flexible, right? You have a major constraint on your routing patterns of only one of these can drive any wire. Okay, anything you like or don't like about any of these switches? Okay, so we can keep going on. If this, yeah.
The capacity is probably, the capacitance is probably the best on this area, just because it's
Yeah.
transistor.
So this one's really small, which is good. Okay, and it's bidirectional, which is nice.
But then I guess, because your transistor scaling, it's kind of hard to control the switch.
It doesn't swing rail to rail. Okay, so that is a pain with this. Like it's going to degrade your voltage. So at some point on the other side, you'll need a level restorer, kind of what we did on the LUT too. So yeah, it doesn't swing rail to rail. A trick that people do, and you saw this in the Chiasson paper, to make this work somewhat better is they'll make the power supply of these SRAMs something like VDD plus 0.2 volts. Okay, so by doing that, by boosting the voltage of the SRAM, you actually make this pass transistor more conductive. And if you put VDD here, so you're trying to pass a logic 1, it gets degraded by VT. On the other side, well, it gets degraded by VT, but it's VDD plus 0.2 plus minus VT, if that makes sense. So basically, I can pass only the gate voltage minus threshold, but I used a bigger gate voltage. So that's commonly done on pass transistors, and it does make them somewhat better, but you still drop some voltage. Does that make sense? You might go, why don't you just do plus 2 volts? Because it sounds like if this is a good idea, why not just make it like even more?
I guess then you have the assumption that then you're creating the transistor itself.
Yeah, it's degradation. So the nice thing about this SRAM is it doesn't switch. This you only change. So this is not a switching node. Like you program this when you power up the FPGA, and then you never program it unless you're doing partial reconfiguration. But even that's low frequency. So unlike most parts of the chip, this has no impact on dynamic power. So it's great. Does have an impact on reliability. If you try 2 volts, you blow up the oxide, your chip dies. But 0.2 volts is usually safe. It makes everybody nervous. Like the foundry doesn't want to say that's safe because it's kind of like, well, what do you mean? Like this is like a 0.8 volt process. You want to use 1 volt? But it basically usually is safe. Yeah.
Is this the reason you're not even considering transmission gate?
I didn't put transmission gate in here, but you're right. You could basically put in a transmission gate, make this a transmission gate as well, and it would be similar. And that would be a reasonable choice too. So now I'm considering it. Good point. And transmission gate it'll take more area. It'll have somewhat more drive strength. It won't drop a threshold voltage. So it's also not a bad choice. Okay, let's go on. So because we're going to see what some of the trade-offs are here. Okay, so let's talk about pass transistors, and the same thing will be true for transmission gate. So if I made this transmission gate, what I'm going to tell you is the same. So nice thing about pass transistors, it's the smallest switch, okay? And it's bidirectional. I didn't mark that down. A really bad thing about it, though, that means you can't use all pass transistors, is it has quadratic growth in delay when it's linked in series. Okay, how many people here know what the Elmore delay is? Okay, so a few people. How many people don't know what the Elmore delay is? Okay, so quite a few. So I'm going to show you the Elmore delay. This is useful for if you're doing transistor level design to get intuition. You want to have a model in your head. Okay, so let's say I have, let me see what I have on here. Okay, so I have a buffer, okay, driving into a pass gate, and that's got it's got a routing wire here. Forget that, just say there's a routing wire here. So there's basically a pretty big capacitance here. And then I go through another pass gate and another routing wire. So there's another big capacitance here. And maybe I'll go through a third one, okay? Before I get to my destination, it's another big capacitance here. And finally I get to my destination, okay? So maybe this is a LUT, okay? So I want to think about, if I make this all with pass transistors, I want to think about, well, what does my delay look like? So to really get the delay, you could spice it. And that's going to give you the real switching delay. But you can get a lot of intuition by linearizing this. So a transistor is a nonlinear resistor. But if I've connected this gate to VDD, which is what I've done, or maybe even VDD plus 0.2, but it doesn't really matter. I've connected to logic high for all of these, because that's what I want to turn them on. Okay, so once these transistors are on, they don't behave like this perfectly, but they approximately behave like a resistance. Okay, so there's an R for this pass transistor, and then it's loaded by the capacitance of this wire. Okay, so this is C wire, and this is R pass. And then there's basically another R pass. I'm neglecting wire resistance. So if you want to take wire resistance into consideration, you'd make this R pass plus R wire. Doesn't really change anything. Okay, then I have another one. Then I have another one. Okay, C wire. And this is my output, right? That's where the LUT is. Okay, so I want to know what my delay is, and I'm going to assume my buffer is really fast. So I'm going to not pay any attention to my buffer. I could include it too, but it doesn't really matter. So here's my input, here's my output. The Elmore delay basically says that an approximation to the delay of this circuit is the capacitance of every node times its resistance to ground, like to the driving point. Okay, so it's basically C wire times R pass. Okay, so I have to discharge this capacitance through this resistance. And if you remember way back to somewhere in first or second year, you actually solved what is the time constant of that. It turns out to be RC. Okay, that'll tell you essentially how long it takes to get to like 0.67 of the switching. So you can basically apply that to these more complicated circuits too. And you take this capacitance, and you say, well, how much resistance does it go through? Well, that's basically C wire times 2R pass. Okay, and they take this capacitance here, and it's C wire times 1, 2, 3 pass transistors in series. Okay? And I could add a fourth in and so on. If I add this up, you'll notice that this is actually quadratic in the number of things I put in series, which is really bad for delay. So pass transistors can be okay for like one routing wire or two, maybe even three. But if you have to go all the way across the chip and you start hooking together like 12 of these, it becomes like insanely slow. Because all of this capacitance that keeps growing as you add more and more wires has to be discharged through an ever-growing chain of transistors, which behave approximately like resistors. So does that make sense? And so this gives a reasonable estimate of the switching time. It's not perfect, and if you really wanted to know it within like 20% or so, you should go spice it, but it'll get you the right ballpark estimate. Okay, so that's why it's quadratic when you link these in series. So you cannot build a routing architecture that's all pass resistors because you have no way to go across the chip in a reasonable way. If you do a high fan-out net, so here I was just doing fan-out 1. If I was doing a high fan-out net, I'd have all sorts of branch points, right? So I'd start hooking in more capacitances and resistances in some big tree, which is going to be really bad, right? When you start working out the delay of that, it's even worse. So you can't make something as all pass transistors. For tri-state buffers, they're bigger and slower for one switch. So if you make one switch and it's not too loaded, it's not this like many pass transistors in series, a tri-state buffer is not as good. Took more area, and because it has essentially multiple transistors in series, in your pull up or pull down path, it doesn't give you as good speed for the same area. But its growth is linear as you hook wires together in series, because basically the capacitance here gets discharged through this pass gate and then this buffer, right? It doesn't keep growing. If you were to apply the Elmore delay to this, it's very simple. It's just linear. It's the same amount over and over again as you have more stages. Okay, so you can make an architecture that's all tri-state buffers, right? Maybe it's not as optimal as you'd like, because maybe for some short connections you could have done better, but it'll work well for long connections and it's pretty reasonable. And there are studies that show that you can do a bit better by mixing them. So if you make 20 to 50% of your routing switches tri-state buffers and the rest pass transistors, you kind of can use the tri-state buffers for longer connections, the pass transistors for shorter, and it works pretty well. Okay, so the direct drive switch basically does the switching before the buffer. So if I look at this, this style of tri-state buffer, which is like a buffer plus a demux, it essentially does the switching after the buffer, which means these have to be big, because they're driving big routing wires that have a big capacitance. If I flip it around and I say I'll choose on the input side who makes it into the buffer, these can be small, because I can make them very close to this buffer, and this buffer usually you would make out of 2 inverters. The first inverter is small, the second inverter is big. So it means that this node doesn't have that much capacitance. So I can make these relatively small, and it's still okay. Okay? And I can now make the buffer, I can choose to make the buffer non-tri-statable. But that's the definition of a direct drive switch. I don't put a tri-state on, because it's a buffer that's not tri-statable is smaller and faster than a tri-state buffer. Okay, but this has, we already talked about it, has a major restriction on a routing pattern, 1 drive point per wire, but it is smaller and faster than a tri-state buffer. And for long connections, because again, we don't have this kind of buildup of resistance, this is still good for long connections, right? Its delay is kind of, if I go through 10 segments, the delay is just 10 times 1 segment. Okay, so that's direct drive wires. We're going to talk about a paper that shows they're a good idea, but let's take a break first. So let's start again at 10.2, okay? I'm past my 10.2 thing. Okay, so I've mentioned these direct drive routing switches a bunch of times, so let's look at this paper that they were kind of introduced in 2 places. They're actually introduced in academic work and in commercial work simultaneously. So we're looking at the academic paper that introduced them. Okay, so this is work by Guy Lemieux, who's now a prof at UBC. Basically what he noticed is that in FPGA routing architectures to that point in time, you always had these what he called bidirectional routing architectures. So your routing switches always let you go both directions. So here are wires coming into some switch block, and maybe we're using tri-state buffers, but we build 2 tri-state buffers back to back. So we can either go from the right to the left, or we can go from the left to the right. But this perturbed him, because he said, under no circumstances can I use both these buffers. So I can guarantee I'm going to waste half my switches for sure, right? In practice, I'll waste even more than that, but I can even just look at them 2 at a time and say I'm for sure wasting half of these. So he thought, well, maybe we don't have to do that. What if we instead made what he called a directional switch block, where basically certain wires have like a predetermined direction. So on the left, he's showing if I build it out of muxes and tri-state buffers, that's the kind of switch he's using. What do I need to make, this is an FS equals 3 switch block. Okay, this is basically a planar FS equals 3 switch block. It's one of the ones we just looked at. You wind up with 6 switches basically where wires cross. And when he actually goes off and builds that, he wound up with this pattern of 4 to 1, I guess, let me think, is that 4 to 1 or 3 to 1 muxes? 3 to 1 muxes So he's got, for this piece of the switch block, he gets 4 3-to-1 muxes and 4 tri-state buffers. And he said, well, what if we, instead of saying every wire could go either direction, we don't know which one, what if I said the odd wires are going to go left and the even wires are going to go right, and the odd numbered wires are going to go down and the even numbered are going to go up? So I've pre-decided on a direction. If I do that, I can basically get rid of a bunch of these muxes, right? So my switching circuitry gets smaller. Does that make sense? I have to actually, to go through, I think what this is, though, is it's showing like for these 2 sets of wires, okay? So he's showing you what you get for sort of a bigger part of the switch pattern. And
It's the same, I think it's equivalent number of muxes and buffers for a larger, like
for double the number of wires. Yeah, it's another way you can think of it. And I think on up here, you lose like 20 IQ points or maybe 30 when you're on the whiteboard. So I'm not going to try to walk through, I trust he got it all correct. And you can intuitively go, wait a second, yeah, that removes a whole bunch of switching options. So I get rid of a whole bunch of mux inputs. I'm going to take it as an exercise for the class to figure out exactly how many. But okay, so and actually, maybe I should just click. So Professor Lemieux says half as many. I think he's right. Okay, half as many switch elements if we pre-decide which direction everything goes in. So what I've given up, though, is, well, what if in some local region I actually really would have preferred to have a whole bunch of wires going to the right? And that could happen, right? I could have a data path where lots of data is coming in from PCI Express and everything wants to go to the right. Well, in that case, I'm going to need a wider channel width because only half my wires can go to the right. So he has given up flexibility, but he's removed a whole bunch of switches. Okay, so if we have the traditional bidirectional wiring, so we already looked at this. At the ends of wires, we have these back-to-back. He's using tri-state buffers, so back-to-back tri-state buffers. And then we also have to have like the output connection block. How do we get out of a logic block? So he's saying, well, you can build that with a buffer and a demux, so a bunch of big pass gates, okay? And I can shut off basically this routing wire here. It can be driven from multiple places. Okay, so it can be driven from its left end. It could be driven over here from its right end. It could be driven by this logic block. And all of them have to be tri-states. Like there's kind of multiple points on this wire where I could be the driver. So everybody's got to be tri-statable or we're just going to fight each other. When he makes this change to say, let's make the routing directional, he can just make that change where he says, okay, let's take out a bunch of switches, and now the routing is directional, but let's keep the output connection blocks the same. Okay, so it's still this buffer and demux, and we still have tri-states on our switch blocks. Okay, so all he's done is kind of removed inputs from the muxes to make things directional. He hasn't changed anything electrical. Both the routing switches and the output of the logic block are still tri-state buffers. But notice in this case, well, this is a tri-state buffer, and I have to do that if, I'm doing that so that basically I can shut off the routing driver when I want to drive it instead from the logic block. But there is not ever, I know there will never be a routing driver over here because I made this wire directional. Okay, so it's for sure nothing on its right end that's going to drive it. I have things on its left end. I can have logic blocks that are driving it at that end or maybe somewhere along its middle. I might have other things driving it in its middle, but I can guarantee there's nothing driving it from over on its right-hand side. So that led him to think, well, maybe I can get rid of the tri-states because I've gotten rid of one of the reasons I had a tri-state, which was maybe I'm driving it from this end and not this end. That's not going to happen anymore. I could basically, instead of having that buffer and then demux, I could take the output of this logic block and basically feed it into some of these routing muxes. Okay, and so we'll select from a bunch of routing wires and also one or more logic block outputs, and we'll decide what drives this wire. And we're going to do that all at one spot. And if I do it all at one spot, I don't need to tri-state this anymore because that's the only set of things that could ever use it. If none of them want to drive it, then it doesn't matter, right? We'll just drive it to ground or something, or some arbitrary value. So there's no reason to tri-state this, because nobody else could ever drive it. Okay, so that electrically is nice. Okay, I got rid of this demux here is gone. Now I did feed into these routing muxes, but the demux had to use pretty big transistors because it's driving big routing tracks that have high capacitance. This mux, its inputs are lower capacitance, right? They're little pass gates. So as long as I don't have to go too far to get to it, I could save area, right? I can use small pass gates here. And so that's a benefit. Also, a buffer is just an inverter chain, right? So it might be one inverter, but more commonly it's a couple. Usually you build like a small one than a big one. It has higher drive strength for a given area. Okay, so it's a better area delay product than a tri-state buffer. So electrically, this is superior. But there's a big connectivity constraint. Okay, so I only have one drive point on this wire. So I can drive it from routing wires that are near this drive point. I can drive it from logic block or other block outputs that are near this drive point. But like only things near there. I couldn't take a logic block over here and say, well, let's feed that in there. I mean, I can draw that on the screen, but what I just did is drag some big piece of metal across my layout. And I don't want to do that. Like, I mean, I basically just made another routing wire, whether I want to call it that or not. Yeah.
Yeah, something that's related to this is when you showed us like the typical routing architecture with island style FPGA, the output of a CLD goes and connects to a channel. Right here, the output connects directly to the switch block.
Yeah, so basically this starts breaking down this notion of output connection block and switch block. They really get munged together into one electrical structure. So you can't speak of them completely independently, although you can still talk about sort of FC out because it's like how many muxes do I feed into? But electrically it is going to now be combined. Does that make sense?
Yeah.
Okay, so he added these architectures into VTR and basically ran them through that full CAD flow and measured what happens. And what I'm showing you is for a bunch of circuits, what area does he get? And he's got everything's normalized to the kind of classic bidirectional with tri-state architecture. He's had to choose a logic block, he's had to choose wire lengths, etc. He keeps all that constant across this experiment. And one would basically be, what do I get with a bidirectional tri-state architecture? So the first thing he does is he says, what if I make the architecture directional, but I don't change anything electrically? I keep using the tri-state buffer style of electrical design. And he gets these crosshatch numbers. And the most interesting thing is the geometric mean. And basically it saved 20% area. So it's a pretty big area savings, actually. If he makes them directional, so he takes the tri-state off, his channel width goes up. Okay, so sometimes he does waste some wires because of the fact that they're harder to get to. But the amount of switching he needs, the switches he builds are smaller, right? So he actually saves even more area when he does that. So that's basically maybe somewhere around 75%. So 25% area reduction. Delay. So here, the directional with tri-states is actually worse. Okay, so the geometric mean is maybe 5%, 4% worse. Because he didn't get any electrical gain. He didn't redesign the switches. And sometimes he's getting more circuitous routes because he has taken some switches away. Okay, so that could be a good thing. But and it was a useful thing for area. Taking those switches away only helps him a little bit on delay. Does make his routing wires more lightly loaded, so they get a bit faster. But that's overwhelmed by the fact that sometimes he can't get his direct-to-route because the routing patterns are less flexible and he loses a bit of speed. But when he basically goes further and makes the wires not tri-statable, he gets about a 10% delay reduction. And it's basically because the electrical design is better now. Okay, so all of his switches just got faster. That overwhelms the fact that he has to have more circuitous routes. Like this is even more significant routing pattern restriction, but it's still a net win. Okay, and if he puts it together into area delay product, it's kind of the one number that you care about the most. It's It's around a 30% win, which is huge, right? So that's a really big win, so it looks great. Okay, so I mentioned this was actually, yeah.
So it just looks like this is always a win. Is there like any downside to doing this? Complexity?
No, it's good.
So
You
it's
should. This is the way you should. If you're gonna pick one thing to do, just do this. So it was a good discovery, actually. It's much better. I guess I'll show you at the end of a few more slides. There are cases where you don't always do this, okay? But if you're kind of going, what's my heuristic? Do I do this or not? Your heuristic is do this, okay? Yeah.
So, in the previous slide, when we said area in minimum transistors, we mean area overall, including the routing area, right? But just in
Yeah, that's a good question. I actually would go back and read the paper. I think his area here is just routing area. Okay, I don't think he's including the logic block area. So if he included that, it wouldn't change. It would wash his gains out some. Okay, but because usually you have more of your area in routing than other things, it'll yeah, you have to derate it by maybe divide by all his gains by 1.3 or something. Does that make sense? Wouldn't change any trends, but it would wash them out a bit. Yeah.
So I was wondering, like, what was the state of art at the time this paper came out? Like, if we went and got the latest Altera or the latest FPGA, did they use bidirectional wires or
Yes, they use bidirectional wires. Okay, so at the time this paper came out, but basically, as he was doing this at the same time at Altera, we also found this. Now, Dave Lewis is Guy Lemieux's PhD advisor, so you kind of don't know. Okay. Like, I think so. It's possible he gave a few hints to Dr. Lemieux. Like, I don't know. Do you know what I mean? It's possible. I don't think that Altera stole this from him. So let's go with that one, or this completely independent. But so Dave Lewis came up with some of these ideas clearly, right? And he's actually on both papers, the commercial one and the academic one, which were done at about the same time. Does that make sense? And so yeah, at the same time that this was being done in academia, we found the same thing in Altera. And so this is a paper on Stratix, which basically was the first Altera architecture to use direct drive routing and to make that name for direct drive routing. So architectures before this didn't do this. So these results basically are an alternative visualization of what I just showed you from Guy Lemieux. Like, they're all basically in agreement with them. So the experiments here are basically on the left-hand side is a mix of pass transistor and tri-state buffer-based switches. Okay, so that's 0% direct drive switches. Here it's 100% direct drive switches. Okay, and this routing architecture has a mix of length 4 wires mostly, but a few longer wires. So here length 16, here length 8. And basically what you see is for delay, this is a delay averaged over a bunch of circuits, direct drive is always a win. Okay, that lines up with what Lemieux found. I guess what we're doing differently here is he was basically turning it on versus off. Here we're basically we're seeing, are there good mixes, right? So all traditional, all direct drive, and basically you want at least some direct drive, but it's never a bad idea for speed. You can go all direct drive for speed. What happens with routing channel width? So if your wires are not that long, so a mix of length 4 and length 8, it didn't do much. This was actually very surprising. So going from a switch pattern that's less restricted, you can use a wire in both directions, to one where every wire can only be driven from one point, didn't actually move the channel width very much. That starts to change as your wires get longer. So here we have a mix of length 4 and length 16. Longer wires, the fact that you can only drive it at one point becomes a bigger restriction. There's more risk of wasting a big chunk of metal. So the bigger your chunk of metal gets, there's more downside. Okay, so the place where direct drive sometimes doesn't make sense is for long, expensive wires, right? We're saying I can only drive this in one spot, may not be a good trade-off. But this was quite surprising. So it turned out the CAD tool could deal with this constraint quite well. And when you put it together for area, so that said that there wasn't too much impact on channel width. Electrically, it is more compact. So it's not only faster, it also takes less area. So basically going all the way, all direct drive actually helped area too. Okay, so to summarize that, direct drive imposes pretty big limits on the switch pattern. You can't drive a wire in the middle of it. Every wire has a direction. But it only modestly increases the channel width if your wires aren't too long. If you made an architecture with all really long wires, then it would probably not be a good idea. The fact that you have fewer drivers per wire reduces loading in the area. The fact that you can get rid of the tri-states makes it electrically superior. So Lemieux found that it was about 9% less delay, 32% less area delay, which is a really big win. So Altera went to switch to all direct drive switches in Stratix and the devices that came after that. Xilinx, one generation later, switched to direct drive, which is, again, like, that's my metric of this was a good idea. If you see one vendor do it, like in this case, academics said it's a good idea, a vendor said it's a good idea, another vendor said it's a good idea, so at that point, it's becoming like orthodoxy. What's that?
How many people does it take to get a good idea?
I don't know, maybe only one, but it actually takes years to prove it's a good idea. You're going to see in another couple of weeks, we'll be discussing hard knocks in FPGAs, like embedded networks on chip. And the PhD student a lot of the key work on that was done by Mohammed Abdel Fattah, one of my PhD students, who's now a prof at Cornell. And I remember as he was doing it, we presented it multiple times at Intel and at Xilinx, and he's like, what do you think the odds are that this gets adopted? And I go, well, we won't know for years. He goes, really? And then like 4 years after he graduated, maybe 3 years after he graduated, Xilinx basically put pretty much exactly, very similar to what he said they put in their chip. And they told us, like, yeah, this was very similar, which I think was quite gratifying for him, but it took years, right? He was like, really? It's like, no, that's how long it takes, right? So you won't know by the time you graduate. But if your committee gives you a hard time, you can come back several years later and say, hey, I told you so. So, yeah.
Just curious, can industry just take academia designs into their commercial products?
If you don't patent it or something, yes, because you're publishing it, right? And then, if you don't open source the code, they can't take the code. But the idea is when you publish them, they are open. If you've patented them, then they can't take them without licensing your patent. At least they can't without possible litigation. So we actually did think about patenting this, but basically it's just too much of a pain. And it doesn't, or not this one, sorry. Altera definitely patented this. Okay. This is totally patented to the max. The NOC thing I was talking about, Mohammed and I thought a lot about patenting it and went some way along that. But you have to think of what's your commercialization strategy. So if you have an idea for a better FPGA architecture and you don't have $500 million, you kind of go, I have to license this to someone. So you have to kind of work out what's the odds of licensing it. And then you have to look at the research agreements and stuff and see, well, if the research agreements already said that they get some rights to it, then it's going to be hard to license it to the people who already have rights to it. So talk to your PhD advisor or master's advisor about exactly what the IP agreements are. So.
Is $500 million in the research budget?
No.
Yeah.
So.
That'd be nice, huh?
Okay, so in some recent architectures, though, you have some long wires that are relatively expensive. I'm going to show this in a few slides, but they're high in the metal stack, and you can't make that many of them. And so those wires are kind of scarce and valuable, so they've actually gone back to using bidirectional tri-state buffers. So you now usually have a mix, mostly direct drive, but the most expensive wires, which are the longest ones, highest in the metal stack, often use bidirectional like tri-state drivers, so you can use them either way. Does that make sense? Okay. Okay, so then actually that leads me into the next thing, long wires. So this is a picture from 130 nanometers. I don't have a more recent one that I had easy access to, but it's already showing that the metal stack is basically what I want to show. So you've got your transistor gate down here. So your transistor looks pretty small. And then you have a contact to get up to the first level of metal, and you have vias to go up higher in the metal stack. So what you're seeing is the transistors actually look pretty small compared to the metal above them. And as you go higher in the metal stack, the metal gets wider, the spacing between them gets bigger, and they get taller, like thicker. Okay, so what does that mean? Well, the wires down here, there are a lot of them, but because their cross-section is quite small, they're fairly resistive. So you can't go too far on them before the resistance limits you and you have to go through some kind of buffer, right? Like a routing switch with a buffer or just a regular buffer, or it gets too slow. If you make it all the way up here, the resistance of these wires is much lower. You can go a significantly longer distance before you have to go through a buffer. But you can't make as many of them, right? The fact that they're wide and have higher spacing means you can't make that many. Okay, so we got these long wires. If we're using direct drive, which we often were, but now sometimes aren't, we also only have one drive point per wire. This means we can't get on it very many places. The other reason we can't get on it very many places, even if you make your long wires bidirectional, so you have tri-state buffers, you've got a long via stack to get up here. So you'd actually rather not kind of come up from too many places to get here because it's blocking lots of your lower metal. So these are kind of your express wires, but they're a bit hard to get to. And you're going to make them long, and they're going to be a bit scarce. Okay? So what is usually done for these longest wires is you build a form of routing hierarchy. So I told you that like we've kind of mostly moved away from hierarchical FPGAs to island style. Doesn't mean we don't use any hierarchical concepts. So there is a routing hierarchy still, but it's more irregular in most FPGAs. So what you can do, so what most chips do, is what Alteros do, and I believe most vendors do, is your long wires connect only to shorter wires, not directed to blocks. Okay, so let me show you what that means. So this is the Stratix routing architecture. Other Altera routing architectures are similar. So we have, in this routing architecture, the main kind of wiring is length 4. That's what 80% of your wiring is. And you go out on a routing switch to get onto this wire, and then you go on so this will be a direct drive switch, and then you have a routing mux to get, or a connection block input mux to get into a block. So you have switches that connect you directly from a block output to a wire, and switches, muxes, that connect you directly from the wire back into the logic block. Okay, so that's what most of the wires do. But we also have these long wires. So horizontally, they're 24 logic blocks long. For that to make sense, for that to be fast, it has to be high in the metal stack so that your metal resistance per unit length is small. But I'm not going to be able to build too many of these wires. In Stratix, they're direct drive, so I'm only going to get one drive point on one end of it. So if I try to hook this up to logic blocks, I'd only have like one logic block that can reach this thing. And there's a high probability it's going to get wasted, right, if this logic block doesn't want it. So what we did instead is it doesn't connect to the blocks directly at all. It only connects to the length 4 routing wires. It also can connect to other length 24 wires. So it kind of has a form of hierarchy. Like a logic block can get to these length 4 wires, which is enough to get to where they need to go a lot of the time. And you can connect multiple length 4 wires together. Or the length 4 wires can get onto this sort of express network. These length 24 horizontally, and vertically they're 16, right? Turns out the layout, the logic blocks are taller than they are wide. So electrically, it's better to make this 24 in this distance and 16 in the vertical dimension. And then you can't get off of this long wire and go directly into a logic block, because that would again imply too many via stacks, right? You'd have to come down all over the place and block all sorts of metal underneath you. So you can get off only at every 4 routing channels, so only at a limited number of points. And when you get off of this wire, you have switches, like a routing mux, that allows you to get onto length 4 wires, okay? And the length 4 wires basically complete the route. Does that make sense? And yeah, this is showing that like at each of these points, you have like a direct drive routing switch. So in the Stratix routing architecture, it was mostly length 4, some length 8, and then 12% of these long wires. And these long wires are the ones that were essentially arranged in this hierarchical way. You have to get onto short wires first, and then you get onto that. So basically, the short wires mean that it's okay to only be able to access this in certain spots, right? The access is more sparse, because the short wires will get you to those access points, right? They're kind of like the on-ramp. As I said, all the switches are direct drive, but in the most recent architectures, because these long wires are really expensive, they've actually switched back to bidirectional, okay? Does that make sense? Okay. So I mentioned this earlier in the course when we were talking about island style versus hierarchical, but I'll throw it in here. So this is results from inside Altera that directly compared Stratix, its first island style FPGA, with Apex 2, its last hierarchical FPGA, and they're in the exact same process. And their place and routage in both cases were like a variation of VPR, okay? So this is like the most lined up comparison that I can think of. Same process, same circuit design teams, same CAD team, and you can compare them. And basically, in terms of, this is basically performance, okay? So in performance, it averaged 40% faster to be island style, and it grew as you went to the biggest designs. And it makes sense it's growing, because hierarchical has that problem of getting these longer and longer wires. So it's actually showing it's not scaling as well. And then on top of that, Stratix took 30% less area. So if I multiply area delay product, I've basically cut it in half, which is a very good gain. So I think this is the most direct hierarchical versus island style, and it shows why you nowadays shouldn't build a really big hierarchical FPGA. Okay. Yeah.
I know in hindsight it's easy to say these type of things, but so does that mean that Apex 2 was a mistake and that it was just Stratix is always better? And if someone were to buy a chip, it's Stratix all the way?
Yes.
Yes.
Altera's internal design teams had made Apex, that was their latest hierarchical FPGA, and they basically hired RightTrack, like the company that came out of the research group here at U of T, to redo the CAD tools for their hierarchical FPGAs, like see could they take VPR and make a better placement and routing engine, and we were able to do that. And then we said these are the wrong chips for our CAD tools, and we convinced them, so they actually acquired us and we designed Stratix. But it's very risky to just say, you guys have never actually architected a commercial FPGA before, but I feel pretty good about this, right? Let's shut down the other design team. So they didn't. So their internal kind of classic architecture design team made their next generation hierarchical design, which was Apex 2. And we had already developed like the CAD tools for Apex, which would work for Apex 2. So that's why you could line up all of these things. Like, it was essentially a risk mitigation strategy for them. Like it's high risk enough to just take a completely brand. They wanted to see if there was a better architecture that would exist, and they're willing to invest in that, but they weren't, I think wisely, willing to shut down the other efforts on the assumption that it would for sure work out, because maybe it wouldn't. Does that make sense? But after these results, they basically said there's no Apex. They actually canceled Apex 3. There was like, the start of that was happening, and it was like, okay, that's shut down. Right? Like you're getting reallocated. And so I think it was well managed actually. The COO did a good balance of where he placed his bets. Okay, so go through a few routing architecture principles. So first one is moderate length wires are the best. So you kind of saw like length 4 wires I like. They show up over and over again. Metal resistance has been increasing, so there's a bit of trend to maybe get a bit shorter. And if you're making switch patterns, scrambled and irregular ones are generally reasonably safe. Really regular ones look nice to humans, but often conceal some sort of blockages that aren't nice. The way a router works is it has to find paths, right? So it starts at a block output, goes to some routing wire, maybe another wire, maybe another one. Eventually it goes into a logic cluster input, and then it has to actually get to like the basic logic elements. So it goes to some local interconnect to a LUT or a RAM or a multiplier input. So when you're looking at this, what routers like, they don't like choke points, okay? So you try not to make any spot where it's really hard to get through one of these stages because you took too many switches away. It's also not super useful to make one of these way easier than the others. Putting lots and lots of switches in, say, this part, and very few in these parts, the router is going to now struggle with this, and it's not going to benefit that much from adding more switches here. So you kind of want to balance your routing flexibility, and you want to make sure that when you consider all these cascaded decisions together, there's enough flexibility. Okay, so what does that mean in practice? So one of the things you want to do is you want to make the block to routing interface similar for all blocks. So we already talked about logic clusters, and you saw that the kind of dominant way people make logic blocks is you have this kind of come into the logic block, you go through some local interconnect, maybe it's a crossbar, maybe it's something less flexible than the crossbar, but it's usually reasonable amount of switchability, and you get to like an input to a LUT or a basic logic element. Okay, so the other thing I get out of this local interconnect is I can connect LUTs that feed each other without ever leaving the logic block. Okay, so my local routing gets me from the inputs of the logic block to my LUT inputs, but also can just take outputs from the LUTs and feed them right back without doing anything. Okay, so now I'm going to make a RAM block. So if I make a RAM block, should I put this local interconnect in or not? Because a RAM block's not going to feed back to itself. Okay, so when I have a logic block, let's feed other LUTs all the time. A RAM feeding back to itself, it's very hard to think, what does that mean? Right? Like I have a RAM where I read some data out of it and that becomes the address for the next thing. Like, is this like some kind of infinite linked list chaser? Like, what is that? So that generally does not happen, right? You don't read something out of a RAM and sort of feed it back to your address inputs or your data inputs. It's kind of bizarre to think of what that means. So one of the reasons that we have this local interconnect, which is to complete some connections right inside the logic block, like output to input connections, doesn't really exist. So should I take it out? Should I just, I don't need local interconnect in the RAM. So what do you think? Amir, you want to get rid of it?
With the outside routing, like when I enter the logic cluster from a pin, I'm not very limited. I can't get anywhere inside the cluster.
Yeah, so you're saying keep it, right? Maybe take away the part that lets you feed outputs back to inputs, because you kind of know that part's never going to get used. But you're saying keep the part that goes from the logic cluster inputs to the essentially RAM primitives, like the RAM block inputs.
I might also just make the FC for the inputs.
Right, okay, or are you saying, or I'll make the FC bigger? What do other people think? Who's with Amir, who's not? Nobody's with you. So nobody's against you either. So that's the right way to do it, okay? So you want to make these all look similar. So some of the reasons you put the local interconnect in a logic block don't exist in a RAM. So one of these was, maybe an input comes in and goes to 6 LUTs. That's normally not going to happen in like your data inputs, for example, to a RAM. Like I bring this in and I send it to 6 different data inputs for no apparent reason. Like that doesn't really happen. I don't connect the output of the RAM back to its input. But by still having this local interconnect, it does mean I can get into, if in my logic block I have to get into one of 18 inputs and then any of those can get steered to the proper LUT, I want to do the same thing, right? Like if I had 18 to a crossbar to let me select between 18 inputs for every LUT, I want to do something very similar for the RAM. And the reason is, from the router's perspective, now a RAM doesn't look any easier or any harder to route to than a logic block. It has the same flexibility. If you didn't do that, if I took out this local crossbar, then I'd have to get to a specific input on the RAM, which is actually quite a bit harder, right? I essentially took away this last, phase of routing, which actually helps me. I took it away. So now it's harder. So if I did do that, I should do exactly what Amir said. I should increase the FC to the RAM block, right? I should go, well, I know this is going to be hard to route to. I'm going to try to compensate for it. But generally, you'll have to compensate. You could do that. It's not an unreasonable thing to do, but you have to be aware you have to do that. Same thing for the DSP block, put a local crossbar, et cetera. So yeah, it's basically hard to make one routing architecture that's going to work well for some blocks where you kind of can swap around the inputs and some where you can't. Because you've said the endpoints are sometimes quite specific and difficult. The endpoints sometimes are more general and easy. So you just try not to do that. Try to make them all equivalent difficulty. Either take some of the local interconnect out of everything or take it out of nothing. So, yeah.
Kind of a silly question. Is there a difference between increasing the FC and having a local crossbar?
There is a difference, increasing, because one of them is an extra stage of muxing. So an extra stage of muxing adds usually somewhat more delay, okay? But it can give you more flexibility in a given area than just making one stage of muxes much bigger.
Gotcha.
We already saw this with the PCIe block. You want to make basically the maximum number of inputs or outputs that connect to a piece of routing channel about the same for these different kinds of blocks. You can play with that within a factor of maybe 2 or so. Like you can make some routing hotspots, but you're trying not to make them too big. And I guess I put Y here, but I think we already went over this, right? It's like that lambda R bar over 2. You don't want to have different blocks that effectively want like different channel widths, right? Or different routing fabrics, because you're going to make the routing channels similar and the switch pattern's probably the same. So if based on your start and end points, some things are really hard or some things are really easy, it's really hard to tune your whole rest of your routing architecture around that. Okay, so early in the course we talked about partial reconfiguration. So I said in partial reconfiguration, let me refresh your memory. Okay, let me turn this on. Okay, so in partial reconfiguration, said we have like some block. Okay, so a bunch of lookup table or a bunch of logic blocks, and I'm going to partially reconfigure it. So take this region A, and I'm going to take what's in there, and I'm going to reprogram it to something else. And it's currently talking to this region B with certain wires. Okay, so this wire comes in here, and it goes over here to some logic block or LUT. Okay, I should really make these go up against each other. Okay, so it goes, let's make this big. Okay, so I want to partially reconfigure this. So I want to basically put something else in here. That new thing I put in has to connect to this region B, which I'm not changing. Okay, region B is already there. It's got a certain routing. This block connects to this exact lookup table. And it connects using certain wires. So there's a wire here, goes to another wire here, another wire here, another wire here, into here. Okay? So when I partially reconfigure this, in order for these things still to connect, I put take all this stuff out, and I put in new, primed logic. And I can basically start, this connection that used to come from over there, I can say, no, it comes from here now. There's a new LUT that does that. But at this boundary, it would have to use the same wire. Okay, so that it actually connects onto the path that gets it where it's supposed to go, right? So this is supposed to be some output. Something in here drives this output, which gets to this input in this other module, but they cross at this point on a specific routing wire. So I'd have to get to this exact routing wire. And I can do that, right? I can tell the CAD tool, okay, when I place and route this new thing that has to go in here, I need a signal to go to a certain routing wire here. So whatever comes out of this LUT needs to go to that routing wire. Is that easier or harder than what I usually get, which is get to this lookup table? So you think it's easier. Why do you think it's easier? I don't mean easier in terms of CPU time, right?
Like, I think it's just, it's earlier on the routing, in sort of configure that. It's like, the block output wire, the logic cluster. Like, you don't have to worry about everything else that happens later on. Just worry about just that one step, as long as you satisfy that step.
Okay, so I think it's easier. Alex, what do you think?
I think it's harder.
Okay, why do you think it's harder?
Let's go against him. Because the set of possible solutions is smaller. So you have less opportunity to go around and take alternative routes to get to block B.
Yeah, so it is harder because basically we have, like, for example, a MUX here that selects from several different, that's your FC input MUX. And then if you have this local interconnect, so we have a style of logic block where we have local interconnect, that's a whole bunch more MUXes. So if we kind of expand it out, there's like a whole bunch of wires around here that could actually get into this logic block, right? And then if I go backwards, I can say, well, then there's wires that can reach those wires and so on. There are multiple ways to reach this wire, right? But it's only got one, usually relatively small MUX. So the total set of wires that can reach it is quite a bit smaller than the wires that can reach this lookup table because there's a couple extra stages of MUXing. So it turns out this is actually harder to do because it's basically more specific. If you only had one wire like this, there's not much congestion in there, it's going to be fine. But normally when you do this, you have buses, right? So you might have like 512 signals that need to make it across here, and you've got thousands of signals being routed here. And all you need is one of these to kind of, I can't figure out how to sort it out, and you've got an unroute. Or you have to take some circuitous routes. You know, maybe it's possible to get here, but I got to detour around a bit in order to get to this wire. So early versions of partial reconfiguration, this is what they did. So when Xilinx was the pioneer of partial reconfiguration. And in their CAD tools for many years, what they did is they basically had to route to specific wires. And that made it much harder in the compiles that used partial reconfiguration because they weren't following, you know, sort of the full path that they would usually use. And then so in Altera, we did partial reconfiguration quite a lot later than Xilinx, and thought we were very clever, because what we did is we said, well, we will never route to a specific wire. If you are going to go between two modules using partial reconfiguration, the CAD tool will insert a LUT that does nothing, okay? It's a LUT just to act as a target. It will pass the signal through. And what that's doing is and we make sure that that comes near the boundary of the region. And basically, it's making it just as easy it's like a regular route, right? You route to that LUT, which is no harder than any other route, to make the partial reconfiguration flow essentially more routable. It was clever, but before we shipped it, Xilinx did the same thing. So I remember when they shipped it, I was like, oh man, it's too bad. so Xilinx does that now as well. But
I guess if like Altera or Xilinx released features sort of out of sync, and you said like out of like maybe one released feature earlier than the other, do you ever like reverse engineer what they did and try to like one up?
you generally keep an eye on what your competition's doing. Okay, so you don't want to read their patents because you don't want to infringe their patents knowingly, but you do want to kind of like know, like, okay, this is in their software and so on. Is there anything clever they're doing? So, I mean, this falls short of like actively reverse engineering things, but you want to be aware of like what are they telling their customers? Is any of that resonating? Are there clever features in their architecture? I don't know if that answers your question or not. So.
Let it be known if I'll look at the camera.
Oh, you were actively told not to read other people's patents, actually. So that you're told, but basically, you don't want to ever violate any like confidential things. So I think it would fall short of like, you know, off reverse engineering what they did, but you do want to be aware of what they did. You certainly had like competitive analysis and so on. Okay, so a few other questions on routing architecture. Which of these two things is better? So do you like the left or the right? They're basically both length 4 routing wires. Just one of them, all the start and end points are lined up, and the other's not. So who likes the left? Okay, a bunch of people. Who likes the right? Okay, Alex likes the right. A few other people like the right. Okay.
It looks nice.
Okay, so somebody who liked the left. Why do you like the left? What do you think? Oh, go ahead.
Because it gives you more flexibility. Example, when one CLB wants to connect to one of the routing tracks, it can directly connect to the nearest one.
Yeah, so that's exactly right. So if I look at, you know, what can I do here? If I want to connect these two red blocks, that's fine. I can use a single length 4 wire. If I want to connect to two blue blocks, I can't, right? I'd have to use 2 routing wires. And the one on the left, which uses the same amount of wiring, same number of routing tracks, I've just got more options, right? I can make both those connections with one track. So in island-style architectures, we stagger the wires, right? We don't start and end them all at the same point. The one on the right basically has like a hard boundary. It's kind of like a hierarchical FPGA, where you have like a certain spot and it becomes a barrier, right? You have to go up a hierarchy level. So try to avoid that. So by scrambling the wire start points, you get more options without any more area. Yeah?
Is the right option even possible when you have direct switches?
Sorry, what do you mean? Like, could you do this?
Like,
Oh, yeah, if you had all direct drive switches, you'd probably have a problem if you couldn't even connect your outputs here because they're too far away from the ends. So let's assume these are not direct drive. So, yeah, direct drive pushes you even more to that. Let's see. I guess we already talked about that, but okay. So I guess another thing I told you is that like you should try to balance the amount of flexibility at each stage where a router is going to make a decision. from connecting wires to wires and blocks to wires and so on. So the cluster interconnect in a lot of academic work, and in a lot of Altera chips at least, has been very flexible, right? So for many generations, a lot of academic work is fully connected, meaning it's a full crossbar. And that was also in multiple generations of Altera chips. So at least some commercial chips did the same thing. So maybe that's excessive, right? Because that's not like a full crossbar is like totally non-blocking, right? Like there's no chance of blocking it. But if you go back a couple stages from one wire to another, there's all sorts of ways this could block. We don't try to guarantee the general interconnect is non-blocking. So maybe that's too much. We made the final stage of the routing problem too easy and it cost us too much area. So maybe we can remove some of that flexibility and save area. And if we do, how much flexibility should we add to compensate? Because maybe if we take it away, we have to add some flexibility, some routing switches elsewhere, but maybe that costs us less area. So this was also looked at in a classic paper by Professor Lemieux. So what he did is he basically looked at the local interconnect inside of a logic cluster. And these dots are basically showing, I've got inputs coming here, and then and outputs from inside the cluster going back. And I have basically a big switch network that connects these inputs from outside and these feedback signals from inside to the inputs of my basic logic elements, my LUTs. And if this is a full crossbar, I'd have dots everywhere. Okay, like every input can connect to every LUT input. But what he's shown here is, well, I've taken away some of the dots. Okay, so it's no longer a full crossbar, which means that the muxes got smaller. So I'm going to save some area, but it also means I might get blocked, right? I might not actually have I might not be able to get all my inputs to all my LUT inputs. One of the things he leverages is the fact that a lookup table, its inputs can be swapped. Okay, so a lookup table, you can change which input the router reaches just by changing the truth table to compensate. Okay, so if I had a function of, A, B, C, D, I can actually reorder those to D, C, B, A, and just change the truth table. So I can tell the router, you don't actually need to get to this input, you just need to get to any input. Okay, and that gives the router an extra degree of freedom. So it's basically got one last stage of switching, which helps it. The other thing he leverages is he uses switch patterns that are the same for every single one of these BLEs. So if you look at this, they're all the same. What that means is that if the router gets to the input of one of these BLEs, it actually, it's basically guaranteed it can get to any one of them, okay, because the switch pattern is identical. He can leverage that to say, I can actually have the router swap around the outputs, okay? Because if it chooses to, instead of using this output, it uses that output, that's fine. Just when I program the FPGA, I'll just swap which one of these I program. And it's guaranteed that that will still be okay. Okay, so that essentially gives him more flexibility on the output side too. So he's kind of added in, he's noticed a couple of patterns that make the router's job easier. Oops, what happened here? He also found, so he found this worked well, but the other thing he found is that for the best results, the number of inputs that he brings into the cluster, which is over here, it's like I, that he should increase that a little bit, okay? Which does actually add a bit of area to the architecture, okay? So that actually is going to add some wires and some switches back in here, but he still found it was a good idea. Resulted in a better area delay product. Why do you think that was a good idea? What do you think?
It's kind of similar to the point of your side earlier, where if you want to reduce flexibility, one way to compensate is just increase the flexibility.
Yeah, that's exactly right. So he's kind of compensating for taking some flexibility out of here. And he also found, since the cluster doesn't usually use all the inputs, and sometimes it might use all the inputs, it's really hard if you use every single input to get them all to the right spots. You now have very few solutions, right? If you basically say, I want to have a few extra inputs, then there are many more solutions. Like you're not trying to find, I have 52 possible wires here and I have 52 signals coming in. It's like I have 56 wires here and I have 52 coming in. Turns out there's many more solutions if you do that. So you can take away a bunch of switches and still make it work out. But if you go all the way to 52 out of 52, you have to find a mapping. It gets much harder. Whoops. So that's basically what I said on these 2 points. What you found is that you can remove 50 to 60% of the crossbar switches. Okay, so you can cut the mux size by 2x or a little more. Now that's not all your area, and it does hurt your routability, so he has to add a few things back in. But he found that for the whole chip, that led to a 10 to 14% area reduction with no hit to delay. It did make the router take longer. So the router now is a more difficult job because it has to route all the way. It basically can't stop when it hits the logic block inputs. It has to actually go further, go through the local interconnect. So there's more congestion and also more things to resolve. So it did take a router runtime hit. But overall, a very good result. In that same Stratix paper that I talked about, it also looked at like basically taking switches out of the crossbar, came to a similar conclusion, but not exactly the same numbers. So by taking half of the switches out, it reduced the area of the chip by 7%. It slowed it down a little bit by about 1%. So it's pretty similar to that academic paper. The reason for the delay hit is probably that the lookup table, you can swap around which input is which, but they don't all have the same delay. Whichever input is closest to the end of the mux tree is fastest. So for this generation, it was basically the slowest input, the one that kind of went through the most muxing. If you think of that tree of muxes, pass gates that forms the LUT mux, was about 400 picoseconds, and the fastest one was about 50 picoseconds. The Cordis router uses that to try to take the critical path, the most time-critical signals, and put them on this fastest input. As you take away some of those switches, you can't always do that, right? You're giving it a more difficult problem where it can't always get to the LUT input it might ideally want. But it's still this is a good trade-off, right? Saving 7% area for 1% delay is a good trade-off. So that's why Stratix also depopulated the crossbar. We found at Altera that you could get a little bit more gain by going below 50%, but it actually got hard to lay out. So it was like, in theory, if you counted switches, going below 50% could still be a little better. But it wasn't clear it would actually be any smaller by the time you really laid it out. Yeah?
I have a question, like, maybe I misunderstood something. So when you say the input of the lookup tables are changeable, it just means you're implementing the function differently. You're making input A input B, right?
Yeah. You're swapping which one you route to which.
And when you say the outputs are interchangeable, it just means implement this function in the other lookup table.
Yeah. Yeah. So with that's exactly right. So you're swapping it around by changing what you program. You're programming a different truth table in to compensate for the fact that you routed the inputs differently here. And you can program, instead of programming a truth table for a function here, you program it there. You've changed which output you're using. Does that make sense? Yeah.
Did Cordis also take it 2 to 7 times hits on the driving time?
No, it wasn't as bad as that. So, there is a hit on routing time, but it's not as bad as that. So, can't remember the exact number. It wasn't anywhere near as bad as that. So, I don't know. This is well coded. I'm not sure. Okay, so this is like kind of Agilex, which you'll read about in a week or so. So Altera's latest chip, and their local interconnect has gotten more complicated. So there's we talked about this a little bit in logic blocks, but I'll talk about it here. Some of the local wires basically can drive all of the ALMs or BLEs like they could in previous architectures, but they now also have some local wires that can only drive a quarter of them. And that's done because even these not super long wires are starting to have non-negligible, kind of delay versus a shorter wire. So it's kind of like they have another half level of hierarchy in their logic block. What else has Agilex done? Okay, so this is like this is from the Agilex paper that you'll read in a week or so. this is the evolution of Altera routing architectures over the last few generations. So in ARIA 10, this is basically horizontal wires and their vertical wires. So the length 3, length 6, and something pretty long. Maybe that's 24. And then the vertical wires, they have maybe, I think that's like 4, and then something pretty long. Stratix 10 shortened the wire some, added more lengths. So you got like length 3, length 5 or 6, length 10, and something pretty long, and so on. Agilex shorter still. Okay, so you can see the trend of the wires are getting shorter. That's because the wires are getting more resistive. You're also seeing a trend of somewhat more wire types. So Agilex has like length 2, 3, 5, 7. I mean, I'm reading this off the thing. You'll see in the paper. So 7 seems a bit odd. So if there's somebody here from Altera, you can tell if that's really a 6 or. But the wires are getting a bit shorter and more different types. The vertical wires are always a bit shorter in Altera architectures because of the fact that their layout is not square, right? So the logic block is physically taller than it is wide. So electrically, you don't want these vertical wires to get too long. The other things that you'll see in this paper is their switch pattern. A lot of it's now driven by locality. They look at like what can they get to, because they don't want big pieces of metal, because metal capacitance is a killer now. So they really try to have switch patterns that are very layout friendly, connect to things that are nearby, but aren't causing too much blockage. They also can't get off these wires except at the end, okay? Which is a big departure from the previous architectures where you could, the short wires at least, you could get off everywhere. The long wires you could usually get off once every 4 units and go onto short wires. Now they're basically only getting off on the end, which is part of why they're giving you more wire types. The reason they're only getting off at the end is it's getting harder to get through all the vias through the stack, right? To get reasonable delay, they have to go, even short wires have to go moderately high in the metal stack, so they don't want to come back down through a whole pile of vias over and over again and block everything underneath them. So basically you choose what kind of wire do I want to get onto and go all the way to the end of it. Maybe you go onto another wire after that, and you get off only at the end. Maybe you have to go backward a unit. But they're taking away the flexibility to get off in the middle. Yeah, and so this is kind of driven by the cost of the via stacks and the higher metal resistance. Shorter wires only get off at the end, more wire types. That was a pretty quick overview of that, but you'll get to read this paper. Okay, maybe I'll pause there. Any questions on anything so far? Okay. Let's see, almost done. Okay, let's see if this is also like violating those principles I talked about. So I said, well, we basically said that one of the things that's not great about hierarchical FPGAs is they created these hard boundaries, like certain places where you were physically close together, but you couldn't connect as fast as physics would allow. You had to kind of follow this hierarchy. Okay, so if I want to connect these 2 red blocks, I can do it with a single wire, so that's pretty good. But if I get closer, this blue box, which is right next to me, I still have to use that same length 4 wire. I could do a bit better if I had, length 2 wires and so on. So a more diverse set of wire types helps me with that. But I still kind of have to leave this block and go here, right? So maybe I can do even better, right? Could I skip all the muxing to go out to the general routing? And so there's an academic paper on that from Professor Rose, actually, where they basically said, well, what if we have connections that don't go all the way out to the regular routing? So the regular routing, the best I can do is I go through some fairly big buffer. I go out through some kind of routing switch onto a routing wire. And then from that routing wire, I go back through an input connection block mux, okay? So the best I can kind of do is, and then maybe I have some local interconnect in the logic block too. So the best I can do is that. And I could make this wire maybe pretty short, but there's still a few levels of muxing here. So they basically added in direct connections, where they said, well, what if I take the output of this logic block and didn't connect at all to any routing wires, I had some connections that just went directly into basically the connection block multiplexers of the wire of the block next to them. Okay, so they bypass the routing wires completely. You're only going to be able to reach the things next to you, because that's just the way you've built it. But maybe there's a benefit to that, because you kind of short-circuited the routing hierarchy when you are physically right beside the next block. And they did find this worked. So they got a 6% delay reduction. It did cost them some area because they're adding some more switches, but it was still a net win. Xilinx does this, okay? So they have something called Direct Connect, which basically from a logic block or other block, you can drive its 8 nearest neighbors in a diagonal pattern without going to the general routing. And it is faster than going to the general routing. It gives you kind of a bigger, it does two things. You can make more efficient connections to these neighbors. It also, if you're willing to hand optimize a lot, it gives you kind of a higher ceiling, right? The automatic CAD tools can use this a certain amount. You know, sort of superstar circuit designers who want to like really micro optimize, it gives them like a higher upper bound. So Altera has something similar. They have, they give it a different name. They call it Direct Link. And a logic block or other block can drive directly into the local interconnect of what's right, immediately to its left or right. So Xilinx can do 8 neighbors, okay? And Altera can only do 2, like the left and right. This might be a hard question. Any idea why? There's actually a good reason why they each chose different things. Yeah.
I feel like it has to do with you don't want to bring the wires in 2 dimensions. If you can just, I don't know, like go in 1 dimension so that maybe you introduce more congestion that way, but you don't have to go in the other dimension. Maybe that gives you better congestion.
It's the right idea. So Xilinx isn't scared of going in both dimensions, and Altera is, okay? Maybe scared is the wrong term, right? I'm not casting moral aspersions on the choice. It's not primarily for congestion. Like, neither of these is an unreasonable choice. But yeah, clearly Xilinx thinks they can get more out of these 8 nearest neighbors, and they can physically reach them all, but Altera only reaches 2. So you're on the right track, but this is maybe tricky. What do you think?
I guess, like, it might just be because of, like, if you have a lot of these, like, neighbor connections, which are very substantially across the entire view.
Yeah.
And then maybe we can, like, just having those left-right connections are sufficient to capture this sort of a similar routing quality compared to the, just like having the 2 possible connections.
Yeah, that's reasonable. So yeah, they're both reasonable choices. Xilinx spends a little more, but they get a bit more flexibility. There's, so they're not unreasonable, but there's an interesting reason why Altera does it this way. Maybe I'll briefly mention, and then we'll end for today. So let me turn off the projector. Okay. Just going to show you this because it's pretty interesting, in my opinion. You'll find certain things that are difference between Altera and Xilinx, where Xilinx tends to not have as much differentiation between vertical and horizontal, and Altera has more, okay? So, and basically the reason is repairability. So Altera architectures, you can repair them because they build some spare rows. So what that means is if you buy a chip, like one of the bigger chips, if you buy the low-cost families, this is not true, but for the bigger chips, like the Stratixes and the Agilexes and the Arias, you'll buy a chip that has like 100 rows of everything, and physically, it really is 104. Okay, so Quartus will tell you is 100 rows of logic, RAM, etc. And the actual chip is 104. And it doesn't have to be 104, but that's a reasonable number. What's done, the reason that's done is that basically as long as 100 out of the 104 rows work, Altera can ship that chip to you. And that actually gives them much better yields, and it's a net economic gain. But you can't actually tell the CAD tools that every chip is different, okay? Because people are not willing to compile their design for every unique chip and close timing and debug. Like, they will not do that, right? It doesn't make any sense. So what happens in Altera chips is basically, okay, let me draw this out. Okay, so let's say I've got some routing. There's like length 2 wires. I'm going to connect these two length 2 wires. I got this block connected to this block. So let's say that's what I did. Connected a length 2 wire to another length 2 wire, and these two blocks get connected. Maybe this row, and I'll draw another row down here. When the chip is tested, all the rows are tested. If a row is broken, a fuse is programmed to say this row is broken. It's a non-volatile fuse, so it can be red when you power on the chip. When you program this chip, if this fuse says this row is broken, you will not put this in it. Okay, even though Cordis said that's what you should put there. Instead, it'll be shifted up one. Okay, so you will put this here. So this is A, this was B. You'll now put A here, B here, wire, wire. Okay? For this to work, this row has to be identical. Okay? Has the same mix, same logic blocks in this and RAM everything's in a column. You have logic blocks here. This is a RAM, this is a RAM, this is a RAM. All these wires are identical. Okay? There's a length 2 wire here, feeds a length 2 wire here. Same thing happens here. So you can basically shift the whole programming bit stream up by 1, and it still works. But one of the things that's now a bit trickier is maybe I had a C block here that used to connect to a D block here. Okay, so that's what Cordis thinks it's doing. It's connecting C to D. Well, D is going to move up 1, so D is now here. Okay? And I used to connect this with like a single, let's say, length 3 wire. Okay, so I came out here and I connected here. And now D actually is up there. Okay, so Altera actually has to make all the wires 1 unit longer than you think. So if you see a V4 wire in Cordis, it's really 5 units long, and it has the same switch pattern at each spot. So basically, it guarantees it can connect there. Okay? So what this means is vertical wires all have to be built 1 unit longer than you actually think they are. And that means they're a bit more resistive, a bit more capacitive, a bit more expensive, because you have to have extra switches, et cetera. For a length 4 wire, essentially it's like a 25% overhead, right? For a direct connect wire, let's say I connected to here. So I thought this was really nice and short, just going right to the bottom of this. If I do that, I actually also need to go up here, okay? So for really short vertical connections, the overhead of you really have to go one row higher and replicate the switch pattern is a higher relative overhead. So that's why they don't do direct connect vertically, because it would be more expensive for them. And also would be slower. In the timing analyzer in Cordis, you don't get the delay of this wire, like a length 4 wire, you get the delay of this wire, because that's physically what's on the chip, right? If you did a direct connect vertically, you would not, Cordis couldn't tell you this is the delay, even though 95% of the time that is the delay. It would have to tell you this is always the delay. And that delay is not going to be nearly as good. So the gain from really short vertical connections is kind of washed out. So they just don't build it. It is quite clever, though. Like, it's basically, redundancy is really interesting, where you start making big chips and you try to think, how can I make a chip with much better yield, but you have to hide it from the software, right? There are academic papers that say, well, what you could do is tell the software exactly what's broken on the chip and rerun it. No one's ever going to do that, okay? People do not like running FPGA CAD tools once. They do not want to run them 10,000 times. But you wind up with clever problems of, like, how do you make the chip do this? Yeah?
So, like, in Altera's analysis, the economic gain of having the repairability is more beneficial than whatever speed up they get from
Yeah.
unit delay to them.
Yeah, the gain is pretty big, actually. So it was done on all the Stratix series chips, all the Aria series chips, I assume is still done. It was not done on the Cyclone series chips because they're smaller. Okay, so your biggest gain is the chip's big and the process is immature, so you have high defect rates. If you're making smaller chips on a mature process, then it generally won't pay off, but for big chips, especially on an immature process, it will.
So does Xilinx have a different repair architecture, or do they just don't?
They don't repair. At least they did not, to my knowledge. They still don't. This is actually hard to do. So I've drawn it here. It looks pretty easy, but it was hard. We basically, when we're designing Stratix, I told you it was the team from Toronto here that designed Stratix, well, in concert with some engineers in San Jose, but it was kind of led by the Right Track team. We just didn't want to do this. We were like, redundancy is too hard, we're not going to do it. And the COO said, you will do it, right? Which was actually the right thing, because he basically said, no, the gains are really big, you will find a way to do it. And that was the right management message, because if he had just said, well, do it as long as it's not too hard, we would have just said, it's too hard. So he just didn't give us that option. And the latest versions of it, this is what was done in Stratix. The ones that were done in Stratix 2, actually, in order to do this, you have to have one other thing. You also have to have tri-state buffers, okay? Because if I shifted this one up by, if this one was broken and I shifted up, I need to have another drive point, okay? So it means I can't use direct drive. And that's what was done for Stratix. You couldn't use it vertically, okay? You had to use tri-state buffers in a vertical direction. On Stratix 2 and beyond, there's a technique that's a bit more complicated that allows you to use direct drive by effectively putting a bunch of constraints on your switch patterns, and the programming hardware essentially remaps which wire is which. But I'm not going to explain it on a whiteboard. It's complicated. Okay, so thanks everybody.